Good morning, and welcome to the South Coast Air Quality Management District. For those folks here in the room, go ahead and take a seat anywhere you like. I'm just going to go through a little bit of housekeeping before we begin our conference. Again, by way of introduction, my name is Mike Kraus. I'm the Assistant Deputy Executive Officer in our Planning and Rules Division. And again, this conference is to sort of address what's going on out there in the world of zero-emission technologies when it comes to applications such as industrial and heavy commercial. We've got a lot of exciting things kind of going on today, and I'll be going over that in a moment. But in the meantime, just so those folks know that may be new to our agency, obviously in our auditorium, so welcome. Just down the corridor there are a set of bathrooms that you're more than welcome to visit, as well as our cafeteria a little further down. So with regards to the actual event itself, as you can see, it's a hybrid event. So folks are here live in the room. Those are also joining us on Zoom. We welcome you as well. This is being webcast, so therefore we're codifying this actually online. So those folks that that weren't able to attend or are interested, or those folks that are attending, or like me who forget a lot, can go back and actually take a look of all the things that we're discussing today. And again, that will be available on webcast online. So and hopefully all of us will be on best behavior since we can't go back and erase. All right. When it comes to Spanish translation, for those folks that are on the Zoom, you can click the interpretation button at the bottom of your screen, and that will give you the ability to have a drop-down menu in English and Spanish. Click Spanish, and there'll be an interpreter that will help guide you through the day. Those folks that are in the room, if you happen to need Spanish translation, you can go to our room CC2. How do you get there? It's just out the auditorium toward where the bathrooms are at. Make a left, and it's the first room on the right. So, and you probably will hear the Spanish translation going on in that room. So if you're more comfortable with that, feel free to go and sit in that room. It's the same experience, just not here in the auditorium, but you'll hopefully have a better experience. Okay, let's see. Anything else I kind of need to cover? Yes. By way of some of the format today is going to be, we will have a group of panelists. We'll have 3 panels, actually: technology, end user, and then our regulatory panel. We'll have a number of speakers on the panel. They'll introduce themselves, talk about the things they're working on, and then we'll open it up to some challenging questions from our moderators. After that, we're going to be wrapping up the full panel hour with questions from the audience. Now, those folks that are on Zoom, you can click the Q&A and apply a question there on through that Q&A. We do have some screeners that will be reviewing those questions. We're going to look for the best ones out there, folks, so make them good, make them challenging. For those here in the room that may want to also submit a question, you'll notice there were blue speaker cards outside when you signed in. If you're interested in commenting here in the room, we're going to do the same. We'll go ahead and have you fill out a comment card, get a sense of what your comment might be, so we kind of see if it's a real good one out there. And maybe what we'll do is we'll mix it up a little bit and introduce you, and you can come up and give us your question live. So, and have some fun with that. Unfortunately, because of the timing of this event, we're not going to be able to probably take everyone's comments. We do apologize for that. But again, you can always follow up with us at a later date, and we can go ahead and follow up with a response. So, okay. I think that kind of covers it. Anything else there? Great. All right. Without further ado, I'm going to introduce to you my colleague, Sylvia, who's from the California Air Resources Board. I'm going to give you a little brief here. Sylvia has been with the Air Resources Board for over 20 years. She oversees a team with local air agencies. She did also strategies, those really critical strategies in the state that gets us where we need to go. So people in California are breathing cleaner air. Yes, she is responsible. She's the gatekeeper of this, and she's been doing a wonderful job making some of those really tough decisions and approving or disapproving or finding those areas and plans across the state that really can make a difference in all of our lives here in our most populous state in the nation. She oversees development also of mobile source strategies as well, even though I understand today we'll be focusing on stationary sources. So without further ado, I'm introducing you to Sylvia Vanderspeck. Sylvia.
Thank you, Michael. So good morning and welcome to today's joint workshop with CARB in the district on industrial and commercial strategies for zero emission. I appreciate everyone taking the time for this important discussion today. So as Michael said, I'm Sylvia Vanderspeck, and I work at CARB, and I oversee the air quality planning throughout the state, including Southern California. And so I just want to highlight that Southern California has been at the forefront for fighting air pollution and fostering innovation and cleaner technology for both mobile and stationary sources. And so while the skies today look clearer, they weren't always that clear. Just to give a little history, in 1989, I moved to Southern California and started working at CARB in the El Monte office, and it was in September. And it wasn't till over a month later that I realized that there were these huge mountains, to the east that you could not see on any day. I didn't know they were there. And I can tell you now that you see those mountains, on a regular basis. So the strides that we've made over the past 30 years are really due to the controls in both the mobile sources and the stationary sources that have been implemented by both CARB and the district. And so even though air quality has improved, there's still a long way to go. South Coast has the worst summertime air pollution problem in the nation, and the residents here breathe unhealthy air. So the path that's going to get healthy air to the residents of Southern California really relies on zero emission technologies, getting as many sources to zero as possible. Going back again, when I started at CARB many years ago, that's when the zero emission vehicle program started. CARB started pushing zero emission vehicles about 30 years ago. And maybe it took a little longer than we thought, but they're here today. And so that's and it's important because these technologies do transfer into larger sources, and it is what's needed here in the South Coast. And so, as I told my mom one time, getting to zero, it's not about an if, it's about a when. And so, I'm happy to be here today to participate in this conversation about zero emission future from stationary sources and industrial sources. Again, the South Coast has really been at the forefront. And so I just want to now say thank you again for everyone participating today so far, and I'm going to hand it back to Michael to give a couple more remarks.
Great. Thank you, Sylvia. Much appreciated. Okay, so bringing up South Coast, AQMD, we were the first air agency actually in America back in 1947. The Los Angeles County Board of Supervisors looked outside and said, what is all this? And where did it come from? And what do we do about it, right? And so that was the birth of the air agency. It was first originally focused just on Los Angeles County. However, as we all learned over time, that air pollution knows no boundaries. And sometimes neither do I. So pushing those boundaries means that you have to kind of have a collaborative effort with those other counties. So we joined up with Orange County, Riverside, and San Bernardino, especially recognizing the fact that as the air pollution that was generated from Los Angeles County migrates over into the Inland Empire, we really needed to be coordinated effort and a coordinated voice and a coordinated strategy in order to reduce those emissions. So this agency was formed in 1977. We have over 400 rules on our books with regards to regulating all sorts of different sources. We permit over around 30,000 sources and about 75,000 individual sources, but this is nothing compared to actually all the sources we actually regulate, because there's a whole number in the millions of sources that we do not actually require a permit, but we're regulating them on the basis of manufacturers and distributors and what have you. And so really important kind of work, and we're trying to keep an open mind on what can be done. As Sylvia noted, in our last air quality management plan, which is sort of our blueprint of how we can meet those air quality standards out there, that zero emissions had some great opportunity. It's here now, and how can we make it work successfully? So we're very excited to have that. Some of this areas that we're talking about today is actually new and groundbreaking because it's dealing with industrial type sources, which is a lot heavier lift in order to achieve those more lower emission numbers. So anyway, we've got a really exciting day with you today. We do have lots of staff here on the left. If, by the way, someone wants to make a comment and those blue speaker cards, if you just get them over there, Isabel and Josh, want to raise your hand? You pop them over there to those guys over there. That would be great. But lots of staff is here to help you if you have any questions or need guidance or what have you. We're here to help. Okay, without further ado, let's kick this off on our first panel. Now, this is our technology panel. We're going to see up here, we've got David, all good, and Mike Morris. As you can see, David's on the California Air Resources side of the table. Okay, that's not on purpose. Mike's here on air from the AQMD. But let's talk about who these guys are. You're like, who are they? All right, David Allgood is a staff air pollution specialist from the California Air Resources Board. He's worked on the state's cap and trade program, that focuses on reductions of greenhouse gases and dealing with that ever so difficult climate change challenge. His focus has been on industrial benchmarking and decarbonization and manufacturing. He has his master's degree in mechanical engineering and bachelor's in physics from UC Irvine. Oh, did I not know that? Okay, he's down here, SoCal. All right, very good. And that's David Allgood. On his right is Mike Morris. So Mike Morris is many a decade here as a planning and roles manager at the South Coast AQMD. Mike's one of our leading managers. You probably see him a lot if you ever come to any of our public meetings, as Mike leads up just a real robust and ambitious rules team that does some really great and innovative work. And right now, really looking into new technology. Mike's kind of a technology freak if you don't know him. He loves exploring new avenues and new ways to do things. And he's very innovative in the rule writing arena as well, creating rules that are not just, reasonable, but, effective and makes sense. So we're very excited to have Mike on our team. Mike leads in many different things. You can read that in the bio. I don't think you need me to read, but he is very diverse, actually, in his experiences with lots of different sources and industry types. So again, we welcome David and Michael as our moderators for the plan. Take it away, guys.
Well, I apologize if I can't keep that energy going. I'm going to do my best, but I'd first like to introduce our first speaker, Dr. Ashwin Salvi. He's the co-founder and chief commercial officer for Atmos Zero. And Ashwin builds on nearly 20 years of clean energy and climate background in advanced, meaningful technology development to drive commercialization. Before decarbonizing the industrial sector with Atmos Zero, Ashwin completed his PhD in mechanical engineering at the University of Michigan. Ashwin then joined ARPA at DOE as a fellow in 2013, where he worked on high-risk, high-reward energy concepts and helped create and manage over $75 million worth of federal programs to de-risk the advanced novel energy technologies. He then joined Acades Power, where he led in the commercialization of novel high-efficiency power generation technology. So thank you very much, Ashwin. Let's hear from you.
Yeah, just so everyone's aware, I asked him to slim that one down. Did not listen to me. So apologies for the lengthy intro. Pleasure to be here. First of all, thank you for the invitation to South Coast and to CARB. I think this is one of the most critical things we can do for air quality, not just in the NOx sense, but also in the particulate emissions sense. So I'm Ashwin, co-founder and chief commercial officer for Atmos Zero. What we do at Atmos Zero all day long are heat pumps, but industrial scale heat pumps that can make steam. We look at steam, you might not know this, but steam actually touches every part of your life every day, more often than you might imagine. From the clothes you're wearing today, to the toothpaste you used to brush your teeth this morning, to the beers you had last night, that all needs steam. And it's incredibly hard to decarbonize steam today because it's all based on fossil-fired assets. What we're doing at Atmos Zero is electrifying that, but using heat pump technology to increase the efficiency of that process, so the cost of running these technologies is equivalent or lower than that of natural gas today. So what you're seeing on the screen right now is what we call Boiler 2.0. It's a modular, scalable, and more importantly, mass manufacturable heat pump that can make steam, and we use it as a retrofit in various different industries from food and beverage, chemicals, pulp and paper, oil and gas, you name it. This is a way to eliminate point source emissions and also be able to eliminate scope 1 emissions, but also increase the efficiency of all your manufacturing processes. Can you jump to slide 4, if you don't mind? I know this is an introduction. I don't want to go through all these things. I just want to leave you with this before we get into Q&A. This is meant to be a plug-and-play solution that can scale quickly, and what I'm showing you here is our first customer. This is with New Belgium Brewing, the makers of Fat Tire beer, based in Fort Collins, Colorado. That little orange box you see, that's where our unit's going to sit. It's a fully external located device. All we do is run power to it, electricity, low voltage. bring it boiler feed water, the same water you give your boilers today. Our unit makes steam, and then we tie that steam into the existing architecture of the building itself. So the retrofit is very quick and very low cost to be able to go and implement a decarbonized solution so you can continue to manufacture the way that you're used to manufacturing. So I'm going to leave it there. Pleasure to chat with you all today. Looking forward to the conversation.
Thank you, Dr. Salvi. Have to say, New Belgium is one of my favorites, so looking forward to a site visit at some point. I'm Mike Morris. I'd like to introduce our next panelist, Dr. CJ Carla, who is co-founder and CTO of Carmen Industries. CJ has spent most of his career in the energy space. He has been working on architecting this heat pump system in his free time for the past 4 years while working at various other startups. He was most recently the head of technology at Antora Energy, a thermal battery company that raised $150 million during his time there. While at Antora, he led a team of 15 people. His focus at Antora was primarily around product architecture development and techno-economics to deliver process heat to industrial customers. Prior to Antora Energy, CJ was the VP of power generation at Heliogen, where he had a team of 30-plus people, including leading development of thermal storage system, power block technology, primarily to service thermal and power needs of industrial customers. CJ began his career at GE Global Research as a senior engineer and supercritical CO2 turbo machinery program manager. Now that's a title. The power cycle program was initiated at GE Research by CJ, starting with a $20,000 internal grant, eventually leading to a $100 million plus step demonstration program funded by the Department of Energy. CJ has 20 plus granted patents in energy, including wind, solar, thermal, energy storage, transportation, aircrafts and land transport, and infrastructure fields. He earned a PhD in applied physics from Princeton University. Welcome, Dr. CARB.
Thank you so much. Thanks for that introduction, and I appreciate the invite here to discuss our technology. So we're Carmen Industries. We're based, can you guys hear me?
There you go. There you
Okay,
go.
is that better?
Yes.
Yeah.
Thanks.
Yeah, thank you again for this invitation. We're very excited to share our technology. We are Carmen Industries, based out of Long Beach, California. A lot of our team is local between Orange County and LA. So we're very excited to be part of this opportunity. If we go to the next slide, our mission at Carmen Industries is to electrify global manufacturing. We're starting with heat pumps as our first product introduction. I think it is pretty well known manufacturing plants consume vast amounts of thermal energy in form of steam and other process heating applications. And majority of carbon emissions from industries actually come from processes that are using heat. Heat as a sector typically is very difficult to electrify because natural gas heat is much cheaper than even electricity. So the bar to meet the techno-economics of this kind of technology can be higher. But we have technologies and capabilities on board today where we can do this at an environmentally and financially beneficial point for our customers. Next slide. Okay, in terms of the problem statement on the next slide, what we see is there are many sectors, food and beverage, textiles, chemicals, biofuels production that use humongous amounts of heat. And this, technology to convert fossil fuels to heat has been the same for the last 150 years. We burn natural gas, coal, or other fossil fuels to generate heat. But in the process, we emit a lot of CO2 into the atmosphere. So it's pretty expensive as a process. On the next slide, we have a summary there. Both financially and environmentally. About 20% of our emissions come from industrial process heating, and it costs industry about $600 billion in terms of OPEX to operate these heating systems. So there is a huge opportunity here if this can be electrified, not only in terms of carbon reduction, but potentially dollar savings as well. On the next slide. So the way we do this is we've developed a very highly modular system. The core of a heat pump is a compressor. We're developing our own compressors in Long Beach. We're leveraging a lot of technologies that have come out of the space industry, notably SpaceX, Rocket Lab, in the last couple of decades. Similarly, technologies that came out of the electric vehicle industry. So both of those are key ingredients into helping us build this Thermal One product. Next slide. The benefits of this product, we are at a significantly lower cost basis compared to competing technologies. So much so that electrification for process heat can be profitable today. We're working with customers where we are eliminating their energy cost by 25 to 50%. And this enables, a potential global savings of several $100 billion once we get to scale. And the second main benefit we provide our customers is no longer CO2 emissions or any other emissions on site. So we use clean electric processing. Next slide, please. We work with either model. So we have some customers that want to buy this asset. They want to install it on their site and continue to operate it. The key benefit that we provide in that space is our equipment is designed for no maintenance requirement. So it's basically install and forget kind of an application where it's designed to run 20 years without any maintenance needs. There are no wear components within the system. So it can be designed for that kind of operation. We have other customers that prefer not to pay upfront, but they use heat as a service, pay-as-you-go model, where we're helping them save energy cost, and we cover the CapEx. Next slide. So in terms of how this is possible is because of the team that we have been able to develop. Los Angeles is probably one of the rare places around the globe, not only in the US, where you can find the right talent to build a multidisciplinary product like this. We have attracted talent from the space industry, the EV industry, as well as traditional oil and gas turbomachinery people to be able to develop this product right here in Long Beach. Looking forward to the discussion today. Thank you.
Well, thank you very much, Dr. Kalra. Really appreciate that talk. And I'll move forward and introduce our next speaker, Dr. Jack Brower. He's at the University of California, Irvine, professor of mechanical and aerospace engineering. He's the director of the National Fuel Cell Research Center, the NFCRC, and the Advanced Power and Energy Program. Dr. Brower is an energy systems dynamics expert in renewable energy, simulation and control, thermodynamics, electrochemical systems, especially in fuel cells and hydrogen. And prior to joining UCI, Dr. Brower was on the faculty at University of Utah, a senior engineer at Reaction Engineering International, and a staff scientist at Sandia National Laboratory. He was also the advisor for my grad program. So without him, I wouldn't be here either. So take it away, Dr. Brower.
Thank you very much, David. I've requested a share of my screen and they've granted it to me. So this is great. I have 17 slides I'm going to present in 6 minutes. So it's going to be fast, but I hope you'll enjoy this because we must adopt more solar and wind and use it directly. This is the most important thing that we must do. But to get to where we need to go, CARB already knows that we need to increase the pace at which we are installing these renewables energy storage systems, mostly solar and batteries, as you can see on this chart. This is the new installed capacity that is going to be required by 2030 and 2045 if we are to achieve decarbonized economy. So how are we doing in this case? Our current trajectory is the blue line that I've drawn here, and these are the projections for what we must do to achieve zero emissions. So we need additional policies, additional technologies if we're ever to achieve our policy goals. Now, why are we not installing at that pace? One of the reasons is we're not installing enough transmission. And you can see here the pace at which we've installed transition over history is not nearly as high as it needs to be if we're going to use the amount of renewables we expect to use by 2050. And we're already experiencing negative prices here in California and in Europe. In Europe, it's between 2 to 5.5% of the time. And we're curtailing already, even though we have almost 40 gigawatt hours of battery energy storage already installed in California today. And this is worth a lot of money. It's almost $1 billion of retail sales that is incorporated in this curtailed electricity. And we've installed battery energy storage systems. We got to install many more, but we must increase the pace of installation. From my perspective, the only way to do that is to add whole new vectors. And the most important vector is the stationary production of hydrogen from renewable and clean electricity. This technology is the new technology we absolutely must begin to install en masse if we ever have a chance to increase that rate and reach our policy goals. This will allow additional end uses and additional transmission and distribution via pipes and wires so that we can electrify everything using hydrogen as the vector. We need it for massive energy storage. If you look at our grid, we simulated this 100% renewable case. Pumped hydro system is not big enough. Cars are not big enough. The only thing that can store energy at the size, the magnitude we need for a highly renewable grid is hydrogen or hydrogen derivatives, some kind of a fuel that we make and use to produce from and to electricity. And really, the separate power and energy scaling feature of hydrogen is what is needed for that massive storage. We also need underground transport of energy to make our system resilient. That's how it's resilient today. It's because the gas system has 2 orders of magnitude higher resiliency and reliability than the electric system. The electric system depends upon the gas system and vice versa. So underground delivery of fuels is known to give resilience and reliability that we need. And then some heavy-duty applications especially require the lightweight feature of hydrogen. Now, I know there's going to be a transport panel. I'm not talking too much about that today, but anything that requires rapid fueling or long range or heavy payload will have a crossover point where batteries are worse or where fuel cells are better than the alternative for zero emissions. There are some applications, though, that have a need for either really high temperature heat or for hydrogen as a molecule for the feedstock, or a gas that reacts with the compounds like it does in steel or cement. Plastics need the H's, so does ammonia. Computer chips need reducing gas. Pharmaceuticals can use the H's. Okay, these kinds of things cannot be electrified. But we can use electricity to make the hydrogen that decarbonizes these sorts of things. Fortunately, we've received 1.2 billion funds from the U.S. Department of Energy to begin the transition here in the state of California using the Alliance for Renewable Clean Hydrogen Energy Systems, ARCHES, as an ecosystem that includes not only the 1.2 billion from DOE, but 11.7 billion in matching funds. And what are we going to do with those? We're primarily going to use them in places where we combust diesel today. They include some stationary applications like ports, port equipment, cargo handling equipment. Those things are considered stationary sources, and it's super important to put that hydrogen into these applications. They also include stationary power generation through fuel cells and gas turbines, which can deliver that resilient and zero emissions electricity. I won't talk about these transportation applications like the buses and trucks, but those are also important for our decarbonized future. Now, why do we focus it on diesel? Because we haven't yet begun to significantly decarbonize diesel applications yet in the state of California. Our electric grid's already half decarbonized. Heavy-duty trucks and ships hardly decarbonize at all. And they're the applications that lead to the greatest health and environmental benefits. We show here in our ARCHES diagram where the sites are, where the disadvantaged communities are, where the air pollution and low income is, and they align. We know that by deploying hydrogen in these stationary and transportation applications, we will have 2,000 fewer hospitalizations, 13,000 fewer missed workdays, lots of reductions in emissions, and 48 fewer deaths per year. This is where we need to focus hydrogen and its applications. So I'm pleased to be here today and would be happy to answer your questions.
Thank you so much for that. And I'd like to remind our audience that you're able to provide comments or questions for our panelists through our Q&A if you're participating by Zoom. And if you are here in the audience, by providing a blue card to Isabel or Josh over on that side of the auditorium where they're waving to you. So our next panelist is Jeremy Keller. He's the Vice President of Marketing Development at Rondo Energy. And Rondo is developing heat batteries to cost effectively reduce the carbon intensity of industrial thermal processes using low cost intermittent renewable electricity. Prior to Rondo, Jeremy spent 10 years at Amoresco developing and delivering energy efficiency and renewable energy projects for commercial and industrial facilities with a focus on water, wastewater, food processing, and biogas projects. He's a licensed mechanical engineer in the state of Washington and has an MBA from Oregon State University. Jeremy, welcome.
Good morning. Sorry I couldn't join you in person. Can everybody hear me? Thumbs up?
Yes, yes.
Great. Thanks for having me. Go ahead and hit to the next slide. So I like to start on what is a thermal battery. It's kind of a new category segment. A lot of folks are familiar with heat pumps. They've been around for a long time, but we're still getting good understanding of what generally is a thermal battery. Simply, it takes intermittent electricity from renewables or through the grid. You heat something up, and then that hot material holds the heat, and then you deliver the heat from that hot material as a direct replacement for natural gas-fired boilers, furnaces, dryers. Next slide. So Rondo's technology is using three 100-year-old technologies. We take clay bricks, we heat those with electric resistance heaters. It's more or less the same material that's in your toaster. We do it the same way that a toaster does. We radiantly heat those bricks. And then those bricks get really hot, and we deliver that as, in a lot of applications, steam. And I'll talk about this more, but we're also integrating a lot of steam turbines into our projects, and we're doing combined heat and power. So we're serving both the industrial process heat load on site, but also the behind-the-meter electricity demand. There's a lot of benefits to that. Next slide. So in the top right corner, the bricks are stacked. The bright yellow lines there are electric resistance heaters. They hang inside of those bricks. The stack of bricks gets hot. You then blow air through those bricks, and then that hot air blows across the traditional boiler. In our case, we use a heat recovery steam generator. That boiler is the same boiler that you would find in like a combined heat and power gas turbine or in a combined cycle power plant. And then that steam is delivered at really any temperature or pressure, can deliver hot water, heating oil, any other working fluid. Because the bricks get so hot, we're really able to deliver any pressure steam. So some of our earliest applications are delivering 5 psi steam, and then the other one is delivering 1100 psi steam. We can deliver superheated steam, really matching whatever that industrial process is, and also retrofit power plants. Next slide. So a lot of the early questions we always get from industry is, well, are you commercial? So the system on the left has been operating in California for the last 18 months and is in commercial operation today. It is a full-scale, full technology demonstration, but it's also kind of a baby heat battery. The one on the right is coming online here in 2025. And that 100 megawatt hour unit, most folks in the industry don't really think in energy storage terms, but that system replaces a 24 million BTU per hour gas boiler. So our heat batteries are really being built for the size of industry. And that's like our smallest model. So we really are designing for industrial heat sizes. Some of the other folks talked about it, but you know, the industrial heat space, oftentimes the thermal demand is 10 times bigger than the power demand. And so a food processor might have a 2 megawatt electricity demand and a 20 megawatt heat demand, and that's 24/7. The biggest facilities, your refineries, your chemical refineries, your mining and mineral facilities, they might have a 20 or a 40 megawatt electricity demand and a 200 or 300 megawatt thermal demand, again, operating 24/7. So the scale of these loads is big. Next slide, please. So this is a little bit of talking about how we do that combined heat and power. So the electricity comes in, it heats up that stack of bricks, and then we deliver high pressure steam through an industrial steam turbine. And that regularly will be delivering power back behind the meter at the facility. And then out the bottom of the steam turbine, low pressure steam is delivered, low pressure, 150 PSI steam is delivered to the industrial process. And the round trip efficiency of that is 95%, which doesn't sound great relative to a heat pump, but one of the big benefits of a heat battery is that you can charge in only 8 hours and serve your demand 24/7. So on the next slide, what that means is that you're capturing the lowest cost price hours of the day. So the gray line is the electricity price for any given day. And then the green line is when the heat battery is charging. And then on the top chart, the pink and the orange, pink is the steam delivery. So we're delivering steam constantly. And then the orange is the power that we're delivering behind the meter. And this aligns pretty well with what we see at a lot of facilities. And then the bottom line is just how you're managing your state of charge. So you're always making sure that you have energy in the battery, but you're charging during the cheapest hours. And that means that you can realize electricity prices that are substantially cheaper if you're participating in the wholesale market than what your industrial tariff might be. Next slide. This is the most important thing to industry. They care about the technology. They care that it's going to work. I guess the most important thing is that it's going to work and that they're going to be able to operate. The second most important thing to them is what is their cost? And in California, this is a really important topic. So on the left, the first bar is what is the cost of steam today with natural gas? And this is just the fuel cost. So that's $5 a million BTU natural gas. It's a little bit cheaper than that today. And then the little gray line there is a $35 a ton CO2 price. If you're going to replace a natural gas boiler with an electric boiler in Southern California, with Southern California Edison's time of use 8 rate, an electric boiler is going to deliver steam, just the electricity costs, north of 150. If you're going to do it with a heat pump that has a COP of 2 on that same tariff, you're up to about 100. And in each of these cases, the demand charges on that bill are nearly half of it. A heat battery, if we were using the time of use rate and we were using only off-peak electricity, would be up around 120 because of the way that the tariff is structured. The demand charges are based off the site's, the facility's peak demand, not on your demand during the load's peak events. However, a heat battery that's participating in the wholesale market could have bought electricity in the cheapest 8 hours every day for around $25 to $30 a megawatt hour in Southern California last year. And a lot of that is because there's so much curtailed electricity during the middle of the day. And then when you integrate combined heat and power into the facility and you're offsetting the retail electricity with a steam turbine, your net electricity cost is even lower. And so your total spend is around 20. On the right, we add the transmission access charge, which in California is a purely volumetric rate. And that's another regulatory challenge in the state. Most other wholesale markets charge for transmission based off your facility's demand when the grid is at its peak demand period. California does it purely on your total annual energy consumption. One more slide, please. So the next thing folks really want to know is, are you deploying at scale? Right now, we're building a gigawatt hour. That's about 80 megawatts of steam delivery globally, which is similar to about 300 million BTUs per hour, excuse me, which is like 270,000 pounds of steam an hour. I'll say that in the industrial heat space, one of the biggest challenges is that nobody uses the same units. And so as you're talking to people globally, you have to switch on the fly between therms and million BTUs and CCF. And Brazil got me the other day with kilocalories. So thank you.
Well, thank you very much, Jeremy. And if any of you folks are on 99 in a small town called Pixley, and you see two massive silos, try to look for the orange O for the Rondo installation that's at that ethanol plant. So we're going to go over a number of questions here, and then we'll be taking questions from the audience. And so our first question to the panelist is just generally, what's the status of our technology and the opportunity for further commercialization? And what is needed for further scale up and adoption?
Sure, yeah. I think that's a very interesting question. What we're seeing is with a lot of our customers, uh, there is actually cost reduction to electrify depending on the process. So you can get benefits of not only eliminating CO2, but also saving money for the business today. But at the same time, I think Professor Brower mentioned we haven't really been installing a lot of transmission. Getting power to some of the customer sites, electric power, can be pretty challenging. I know there are national and state level programs that are working towards it, but that's definitely one bottleneck to electrifying every industrial site. If you think of industrial facilities, it's very interesting. You know, most of the industrial facilities are actually the facility cost itself for manufacturing equipment. It's not the major expense. These facilities are processing raw material using energy. So they are processing electricity or energy and raw materials. So getting energy to site is pretty challenging typically because of the amount of energy they use. And most of this energy is actually used as heat. So if now you're electrifying it, you're converting the gas line to an electric supply line. Heat pumps to some degree can benefit because they can reduce the amount of power you need to bring in because their efficiency is typically more than one. So we're reducing the absolute energy consumption. That helps a bit, but still you have to bring in a lot of power to sites. That's one of the challenges. I think in general, this industry is turning a corner right now with electricity getting cheaper with renewables. Lithium-ion batteries are going to play a big role as well. So we're at that transition point, but definitely a lot more support around getting power to sites, transmission would definitely be helpful.
Yeah, I'll jump in. I think those were great introductions to all the technologies out there. Just want to highlight what CJ just said. Heat pumps are the way to reduce energy consumption for your facility. They often operate at efficiencies greater than 100% because what a heat pump does is it moves heat from one source to another source. For the example, if we're at Atmos Zero, we can either be an air source system or a water source system. That means we're either cooling down air or cooling down water, taking heat from there and upgrading that to make steam to be injected into your process. This means you have a dual benefit. You now have heating that you're looking for steam, but now you can also benefit from the cooling side of things. So most industrial facilities need cooling for chillers or for some other process. And to be able to provide both steam and cooling, they now need to have a boiler, a chiller, and usually some sort of cooling tower. A heat pump can reduce the need for all of the different capital with one unit. And so what Atmos Zero is doing is actually commercializing that unit as a standard product. We're not doing a custom engineered solution per facility. When you do that, that ends up being much more expensive in terms of deployment. You have to do a lot of engineering costs, a lot of facility shutdown to do that kind of stuff. We're standardizing this process, this product, and we're actually scaling that with our manufacturing facility based in Colorado. We have a 100,000 square foot facility there to meet the customer demand that we're starting to see. Our first commercial product is going out the door soon, but now we also have a number of units going out through the end of 2026. We're actually an international company. We have a subsidiary in Europe. Just to show you, like, it's a heat pump. Like, these things are well understood. We're not reinventing the wheel here. We're just putting the wheels on the ground and putting it in an application it's never been done in before to be able to help industry decarbonize. So we're very much at that front end of this commercialization, getting products out the door with technology that's really well understood. So the risk is very minimal to our customers. And I'll add one more point to that. Almost all of our customers are deploying our systems in parallel with their existing assets. So they have natural gas boilers today. We can deploy our systems, 1, 2, multiple at their location, and keep their existing boilers there. So we can do things like price arbitrage. We can do things like avoid demand charges or coincident peak charges and keep the cost of operation low because now we can play back and forth with what unit is on when. So we've got a system that can run 24 hours a day if you wanted to. We can have a system that can respond to electrical demand charges and turn off and turn on another asset to make sure that facility doesn't lose steam and you can keep manufacturing.
Let me briefly speak to the fact that we need to deploy more and more of all of these technologies, in particular those that can use electricity. We're talking about all of those here today. But when it comes to hydrogen and fuel cells, the topic I introduced, there are commercially available technologies that are out there. They are typically more expensive than the alternative, and that's primarily because they haven't been built at scale yet. So that's the first thing. Scale economy. Second is that we need infrastructure to connect them. We don't have, for example, a network of hydrogen pipelines yet, and that is going to be necessary to make it cheap. Okay. Third, we do need innovation still. So there are some emerging hydrogen fuel cell electrolyzer technologies and some emerging distribution systems and the like that must be invested in for commercialization into the future. But it's primarily scaling what we already know how to do.
I'll just go back and harp on what a little bit of what I put in my slides, but like the biggest barrier to deployment in California is the legacy tariff structure and the CPUCs and the utilities and how they structure the demand charges. You know, you really need a tariff that is a pass-through of cost causation and allows flexible loads to realize those low value hours of electricity without being penalized for being a large load. You know, deploying flexible load means that you can integrate more and more renewables into the grid because you have something to soak it up. But that electricity has to be able to be purchased at a cost that is cost competitive with natural gas plus the state's carbon price. So that's where we spend most of our effort in California and what holds us back from deploying. Our earliest projects are being deployed with completely off-grid renewables, exactly for this reason, because of those tariff structures. Non-coincident demand charges are a historic legacy, and it needs to be revised.
And there are precedents. They have applied this to other technologies. They should include these.
And it's not to say that, you know, these new technologies shouldn't pay their fair share of transmission and distribution and grid charges. They absolutely should. It's just about making sure that you're aligning those tariffs with cost causation and then moving to a structure that incentivizes electrification instead of disincentivizes it. You can't ask to reduce emissions if you're going to quadruple or quintuple their cost of heat. They're just not going to do it.
And Jeremy, do you mind defining some of those charges you mentioned, like demand side charges and some of the others?
Yeah, sometimes I'm way into it and I forget. So when you look at a standard and like a commercial and industrial electricity rate that the CPUC sets with the utilities, you have what is called a volumetric charge, which is typically like $1 per kilowatt hour rate. And so that's based off how much electricity you consume. Historically, on the bill is also a demand charge. And a demand charge is based off if you have a facility, what was your peak load for your peak 15 minutes? So let's say you have a facility that has an average load of 500 kilowatts, but you have some large piece of electrical equipment that runs every once in a while, and you peak to a megawatt for 15 minutes once in a month, you pay at the megawatt. And so those non-coincident demand charges essentially say, what was your facility's peak load on the grid? When you look at wholesale markets and how ISOs typically charge the utilities that are serving customers, they actually charge those utilities based off of their peak demand when it is coincident with the entire grid's peak demand. So on those highest heating days. And that's how MISO does it. That's how PJM does it. It's how ERCOT does it. And oftentimes, yeah, so that's the difference there. California still has transmission costs and distribution costs pass through, and they merge it into a bunch of different fees in the bill that you see, but they basically break it down into, you know, a time of use rate for your dollar per kilowatt hour, and then also time of use rates for your peak demand. But just for your facility, and it's not tied to the grid's peak demand. Was that helpful?
Yeah, thank you, Jeremy. And I just had one follow-up question for Dr. Brower. Has advances in battery manufacturing, anode, cathode, electrolyte, have those been able to feed into advances in fuel cell or electrolyzer manufacturing as well?
Nice question, because both are electrochemical systems that have similar manufacturing techniques. On the other hand, it's very difficult to use similar techniques because of the very different material sets involved. So while battery technologies have been benefiting by the scale of deployment, we don't yet have nearly that scale. It's at least an order of magnitude less for fuel cells and electrolyzers. So we still have a need to scale that technology. It can learn something, though, from the battery systems.
Thank you for that, and excellent conversation. Our second question to our panelists: what are our best opportunities for cleaner power at industrial sites?
More on-site renewable. Energy storage is great, on-site renewable. I mean, the California grid is phenomenal. I love it here. We talked about 50% renewable. I've seen days it's more than that based on renewable assets and consumption, of course. Being able to leverage that, store that, Rhonda's got a great technology to store intermittent renewables, and being able to utilize that, not necessarily in just like a one system fits all, but maybe combinations, right? Maybe it's not just energy storage, but it's energy storage coupled with a heat pump, or energy storage coupled with a hydrogen generation facility that can help increase the traction of these renewable generation and the intermittent nature of those.
One of the things I think that we all talked about was just how large the thermal demand is for these industrial facilities. And I think it's, on-site generation is important, but they don't have big enough roofs and they don't have enough space in a lot of cases. When we look at industrial sites across California, about half of them are located in rural areas where there is land nearby and they can build the 20, 40, 100 megawatts of solar that they need to provide them the energy to replace their natural gas that you're using for steam or heating. But there's a lot of industry in LA that just has no space. And so you are going to be siting renewables where they can be built and where they fit, and then bringing that back to the load through the grid. Not to talk about competitors too much, but there is work with geothermal and enhanced geothermal and they've been talking about being able to site new drilling at the industrial load and provide heat for that as well. I think that's still really up and coming, and it'll be exciting to see if they can really make the promise of having flexible siting for geothermal practical. But what we see today is really for electrifying, there is some opportunity to build renewables. I'm going to get on my soapbox on one more piece, and I'm sorry, Jack. A major inhibitor to this is that the utility monopoly rules don't allow you to have renewables on parcels that aren't adjacent to your site. So if you want to power your own facility with renewables, you need to have it on land that is right next door to your facility. And because these power demands are so huge and you need hundreds of acres for the solar, you really need to be able to site it locally and then build new private distribution to get it back. And so there was legislation last year to enable that, to expand the exclusions in Section 218 of that, to really allow industrial facilities to build new generation and bring it back to their facility on private transmission lines. And that's a really important enabler for decarbonizing these facilities, or fixing the tariff structure on how transmission charges are, either one, but both are really important.
Yeah, I want to support also local development of electricity production is super important, and we should do as much of it as possible. This is the most efficient way to deliver the electrons right next door. On the other hand, I want to agree with Jeremy that you can't always do that. And secondly, want to point out that many of these industrial facilities can actually be good citizens and actually demand the most when there is the most available on the grid in general. And in this kind of storage mechanism, actually help the grid install more renewables in general. Okay, so this is a huge opportunity for these huge demands, okay, to just synchronize them with the grid and be good citizens on the grid. And our technologies, the ones that we're all talking about here, have a very big role in supporting that, because you can't tell the industry to stop doing things, but you could, with storage and these technologies we're talking about, make that demand dynamic from the grid's perspective.
Overall, I think that that's the biggest thing when you think about decarbonizing industry and electrifying it is, they're flexible loads, they're dispatchable loads, like what AppZero talked about with heat pumps. And big, but being able to shed during peak demand events and having the natural gas boiler coming online, but you're still reducing natural gas emissions by 80–90% annually, right? Like that is those low cost pathways, but it does require utility rate structure reform and processes and thinking about what a flexible load is. It's really different. When you say load, everybody thinks you need electricity 99.99% of the time. And a flexible load doesn't. It wants to buy it, 8 hours a day, that sort of thing. And it's even really different than how demand response has been thought of in the past. So it's not demand response in the traditional sense.
Well, thank you for that. Just going on these technologies and these installations, do they require a total revamp of operational design, or are there areas that these can be used in retrofit applications? Additionally, a lot of these technologies are electricity focused, and so does that require whole new transmission into the industrial site or commercial site?
Maybe I can go first. So that's one of the requirements we imposed on our product design. Like a lot of the opportunities we see today are retrofits or brownfield opportunities. You may not get a lot of greenfield opportunity because these plants have been operating for decades. In such a scenario, we have built a technology that is highly modular and scalable, so we can get our unit very close to the process. So process integration not only becomes easier, but also way faster. Some of the competing technologies, if they're building a heat pump on site, it can take them somewhere between 6 to 9 months for site integration. We are hoping to get these done in like 2-week period, right? Once the unit shows up, all you need is plumbing connections directly into the process. There are some secondary benefits to this. If you can do it at a process level instead of at a plant level, you can match the temperatures exactly. The heat pump performance basically depends on what temperature lift you're asking for. And if you can do it exactly at a process level, you get the maximum efficiency out of it. So there are certain benefits, but getting power to the site is definitely a universal concern across the technologies.
And with getting power to the site, is there some sort of buffer that is on the grid side? Like if you have a connection for 1 megawatt, can that go to 3 megawatts without more installation, or are they 1 megawatt is their max?
So a lot of industrial facilities, they have sometimes excess capability, especially when they bring a new power line in, they try to bring more capability. But a lot of times what also happens is if you want to get more power to site, the substation may not be rated for it. And the way, I'm not a grid engineer, but the way I understand this works is if there is a new facility that needs more power and now they have to upgrade the substation as well, the customer gets charged for all the upstream costs as well, to a very large degree. They do get compensated later on if more people draw power from the same substation. But it's a big, in certain cases, it can be a big capital investment to get power because you're not only upgrading for your own facility, but you have to pay for the substation in certain cases as well. So it's a very, a tricky situation outside of the facility.
I think that the general answer is that you're going to need to upgrade your electrical interconnection supply. And again, it goes back to that rule of thumb of your thermal load is 10 times bigger than your current power demand. So when we're looking at our heat battery projects, we're typically looking at interconnecting to the transmission system. And so we're not connecting to that existing distribution grid. So we're going to be connecting to 70 kV and above.
I'll add on top of that, beyond just the electrical, I think, it really depends on the facility itself. A lot of my customers have enough electrical capacity. This is one of the advantages of having a high efficiency system. You just don't need to draw as much electrical. There are absolutely some customers that do need to upgrade electrical, but the upgrades that they would need to do would be significantly less than something like an electric boiler would require, right? The other aspect of this, and I think we all kind of have the same technology that can do this, is if you look at some of these facilities, CJ mentioned it, these are hundreds of years old possibly, and they've just kind of been hobbled together and built up over time. And so being able to just integrate without having to change the infrastructure of this facility, without having to go and like dig in for waste heat in one location and upgrade it and put it somewhere else, just to be able to tie in and keep everything else the same is hugely important for customers. Doesn't change their manufacturing process. They don't have to change their recipes or whatever like that. If you can tie in without disrupting anything else in the facility, that's a win.
Yeah, I mean, one of the things about the heat batteries operating at the higher pressures and temperatures is that you're able to tie into that existing boiler plant. A lot of facilities will run high pressure steam at their boiler room, distribute it at high pressure, and then step it down to a lower pressure at their end use. But with our high temperatures, we're able to integrate right at that existing boiler header. So you're not having to integrate or change anything downstream. Broadly, I said in my presentation, a heat battery can do any steam pressure, any hot water, any heating oil. As you start to get into the higher temperature applications like calcination of like cement or steel or some of the some drying applications, you are going to have to look at the process more closely. And a little bit of that is just today, a lot of that is natural gas that is directly combusted. And the heat dynamics inside of that process rely on those very high temperatures of combustion up over 2000 degrees C. And so when you go to a lower temperature source, even if you're delivering hot air at 1500 C for a process that runs at 1500, your reactor just needs to be bigger. Now that's way in the weeds of process engineering, but at the highest temperatures, there is some changes in dynamics. And so you need to look at it really closely, and you need to get your process engineers involved. But if you're doing steam or hot water or heating oil, it's really easy to be a drop-in project that doesn't impact the facility's operations at all.
Thank you for that. So we do have a audience question from Aiden, and it's first to Ashwin and then to Jeremy. For Ashwin, can you give us a sense of why New Belgium was interested in adopting your technology? Is it cost, efficiency, greenhouse gases? What was the reason?
Yes.
Oh, sorry.
Yes to all of that. New Belgium is an awesome company. They're trailblazers in brewing. They're trailblazers in actual, environmental stewardship, things like that. Absolutely motivation for decarbonization, elimination of Scope 1 emissions, cleaning up their products. Signature is very important for them, as well as, of course, cost, right? Efficiency, cost. How do we make sure that we are able to give our customers the products they're looking for in a responsible way without having to impact the cost of operations to do that? But that doesn't just apply to New Belgium. That applies in general to all the customers that we're talking to. They all have an imperative, a motivation to decarbonize manufacturing operations, whether that's ESG, environmental stewardship regulations, internal motivation, or the customers are demanding it. That's part of the reason as to why they're all interested. And I think it's great. And this is part of the other reason that we're a global company, because this is a global problem. This is going to be a solution that we need to develop and demonstrate all over the world.
Thank you for that. And for Jeremy, what is the application that you were discussing earlier? And can you also provide why they decided to go with that technology?
So for our first installation in California, it's at an ethanol plant. So ethanol in the state of California with CARB, with the low carbon fuel standard, has a strong carbon incentive to decarbonize. So the economics are attractive for them to replace their natural gas steam with electrified steam. So that was also, I'll say that ethanol generally has a bad reputation. However, they are typically technology forward relative to a lot of other industries. There's still a little bit of a cowboy out there, and so the ethanol plant is generally a little bit more open to trying something new than maybe a different facility. So when you're looking for your first customer, finding somebody that is willing to be a little bit of a really to take on that first installation as you're walking into it. It's, you know, those are pretty important customers to find. So but that is why why ethanol is an interesting application is California's strong carbon price through the low carbon fuel standard program provides an extra incentive for them to do that. And then our other customers are similar. We also have customer Eastman Chemicals who is doing it because one of their downstream customers is asking them for a lower carbon intensity plastic product. Diageo is doing it on their Wistigate distillery because they've made a commitment to 2030 carbon emissions reductions, and they were looking for the lowest cost CO2 reduction pathway. And then in Europe, broadly, where our other projects are, they have a carbon price, but also I'll just say culturally, Europe is decarbonizing. They've decided it, and so they're just looking for the lowest cost solution. And then the other major difference in Europe is that wholesale market really has the access that makes it really easy to get electricity supply and get the flexible pricing that you need. We can get 6 quotes for electricity in Europe within a week of talking to a customer, where in California, it's a 12 to 24 month process to even get access to the wholesale market. So, you know, velocity is really important when we think about where we're going to go for our projects. We really want to build more in California, but Europe makes it a lot easier, which is a little bit of a funny thing to say.
Wow, it sounds like we really need to get the electricity prices, handled. And I think this question is about that. Typically, the change out of natural gas boilers to an electric equivalent will cause operating costs to increase because electricity, especially in California, is very expensive. Dr. Kara, you mentioned that operating costs for your systems can be less than natural gas boilers. And if you could explain that some more, please.
Yes. A heat pump is typically, Ashwin mentioned this, moving heat from a lower grade source to a higher temperature source. So it's not generating heat or converting energy from one form to another. It's moving heat. A lot of the industrial processes, as an example, let's say distillation, the way they work is they use heat to evaporate a fluid and then recondense it at the other end. So whatever energy goes in at a certain temperature, let's say 160 C or 300 F in this case, it is released back when you do the condensation at 200 F. So ethanol plants, for example, the ones that Jeremy is talking about, if you go and look at a plant, they have massive gas-fired boilers to make the steam that is used for processing corn into ethanol, including for distillation as one of the processes. At the other end of the boiler system, they have a air-cooled fin fan cooler, right, where they're rejecting heat to the ambient. What a heat pump does is it recirculates that heat back into the inlet. That kind of recirculation is not possible with a natural gas boiler. The natural gas boiler is a one-way system. You produce heat at a higher temperature, and then you reject that heat at a lower temperature from the process using a fin fan cooler. Whereas a heat pump recirculates it back in. So when you're mostly recirculating the heat back in, you just need to add a small fraction of that energy as electricity that enables you to pump the heat back. And in applications that we're considering, especially high temperature steam requirements for food and beverage, we're able to do this process, recirculate 80% of the heat back, which means you now only are adding 20% of the energy back in. In fact, one of the large studies done by, Tesla was part of it. They presented last year at their investor day where they said the overall heat consumption, energy consumption for heating applications in this 200 to 300 C range is on the order of 15 petajoules a year. And with the right use of heat pumps in this temperature range, we can bring that absolute energy consumption down to 5 petajoules per year. Right, so that's a significant reduction in absolute energy consumption. So now what it does is, let's say you have 80% heat being recirculated. and you're only using 20% of the energy. So even in areas where electricity is 5 times as expensive as natural gas, you're now breaking even on OpEx. But in most places in US, it's a 3x delta between electricity and natural gas pricing, at least for industrial use. So when you're going to a 5x reduction in energy consumption, you now have that 40% spark spread to play with, right? And that becomes your OpEx reduction.
Great, thank you. Thank you for that. And we're getting towards the end of our panel. We have several more questions, but we're going to ask one more live, and then we will try to circulate the questions to our panelists and get back answers for those remaining questions at a later time. So the final question is for Dr. Brower. To transport hydrogen, would a new pipeline system be required, or could it be blended with natural gas and separated close to end users, or used to lower the carbon intensity of existing fossil fuel? I heard about a Southern California Edison plan to use a power plant in Utah to generate hydrogen from excess seasonal renewable electricity and store it in salt caverns. Could existing natural storage like Aliso Canyon be used for hydrogen?
So very briefly, that plant that they are referring to is a Los Angeles Department of Water and Power plant in Delta, Utah. And they are indeed doing exactly what the questioner described here. Using excess renewable electricity to go through electrolysis to make hydrogen stored in salt caverns and to use it in a gas turbine combined cycle plant to make electricity again on demand. Pretty cool project there. Chevron's a major investor in that, and there are others. When it comes to the transmission and distribution of hydrogen, when we have a very large market for it, there will need to be pipelines. And so I'm happy to see the questioner ask about that. Purpose-built pipelines already exist throughout the Gulf Coast, throughout our port complex, and associated with the refineries in that same area here in California, and many places around the world. We have over 500 miles of pipelines here. We have over 1,000 miles of pipelines in Europe and in various other places around the world. So we know how to build purpose-built hydrogen pipelines, and they're going to be important. But if hydrogen is going to be used as the Department of Energy and as ARCHES, the California Regional Hydrogen Hub, expects, we're going to need way more hydrogen pipelines than we currently have. And transforming existing pipeline networks and using the regulated utility infrastructure that we've invested billions in, okay, is the cheapest way that we could transform them into hydrogen, and blending is the way to start. Okay, so there's a lot that I had to say there. Okay, but the key idea is we're going to need pipelines and geological storage to make hydrogen cheap enough, okay, to be used for these types of applications. Finally, someone mentioned Aliso Canyon. The salt caverns in Utah and all throughout Texas have already been proven to safely and effectively store hydrogen. On the other hand, depleted oil and gas fields like Aliso Canyon haven't been proven yet here in the United States, although there have been some tests in Europe that suggest it can be stored in those too. So with an appropriate investment and an appropriate investigation, it's possible that the depleted oil fields can also be used for hydrogen here. Let me say, direct electrification is always better than going through the hydrogen route. Okay, so if you can directly use electricity, please use it. And then we still need all that hydrogen that I'm talking about.
Thank you for that.
Great. Well, that concludes the technology panel. Let's give a little round of applause to our participants. Really appreciate, it's really great insight. I mean, My takeaway from a lot of this is that there are clearly plenty of opportunities out there. We heard a variety of different types of opportunities out there in the industrial sector. It's obviously going to be growing on from as we continue to, and these great companies continue to work on new ideas, or in the case of Dr. Brower, the work that he's doing out there on the front on the academia level as well. And again, we're just really super excited about hearing from that. I know Mike is more excited, however, about the brewery. So I expect Ashwin will be getting an invite out to him soon. We sure hope so. Okay. Again, as Mike had said, unfortunately we were not able to address all of the audience questions, but we do hope to do a follow-up as well. Okay. Again, thanks everybody for that first panel. We're going to take a quick 5-minute break if anyone needs a bio break down the hallway, so we can get ready for the next panel, our end users. So hang in there. We'll be right back.
to Cal Poly Pomona
Sure,
right here.
sure.
And
All right, we're getting ready to start our next panel. If everyone can please take a seat. All right, I'm going to go ahead and introduce the moderators for the next panel. So first, we have Mark Cipolla. He's the chief of the Cap and Trade program at CARB, where he oversees the teams that design and implement the economy-wide carbon market in California. He also oversees the team charged with developing California's net zero cement strategy under Senate Bill 596. He started his career working at an auto plant, and prior to working at CARB, he conducted research on airflow and pollutant exposure at 2 Department of Energy labs. Mark has a doctorate degree in environmental engineering, and he is a licensed chemical engineer. Our second moderator, and most important also, is Heather Farr. I just picked CARB first, you know. Sorry, is Heather Farr. She is the Planning and Rules Manager for the South Coast AQMD. Heather's current responsibilities include developing rules to reduce NOx emissions from commercial and residential building appliances and toxic solvents used in coatings and solvents. Heather has also worked on refineries, refinery flares, non-refinery flares, and commercial baking ovens, reducing VOCs from coatings and products, controlling PM from metal recycling operations, and fence-like monitoring requirements for refineries and related operations. So thank you. And so we will get our next panel going.
great, thank you. Thank you for that introduction. And I will start introducing our panelists. The first panelist we have with us is virtual. It's Joe Brothman. He is the Director of General Services, joined UCI Health in 2015. Joe oversees a team of over 200 professionals who manage the organization's portfolio of properties, including all aspects of building maintenance, management, and compliance, coworker safety and emergency management programs, as well as parking and transportation services. He serves as president of the California Society for Healthcare Engineers Orange County chapter and a member of the California Hospital Association's Emergency Management Advisor Committee. So glad you can join us here today. You should be able to begin.
Great. Thanks so much for being here. Thanks so much. Would you like me to give a little bit of an overview of our new campus and what we're doing here?
That would be great.
Great, wonderful. Well, thanks so much for having us. As you can see here, we're going to just give a short overview of the exciting new campus that UC Irvine Health is building here. So the new hospital that UC Irvine Health is building is in Irvine, California, on our main campus site. It's a good overview of where it's located. So if you're not familiar, Irvine is in Orange County, beautiful location, right on the campus of UC Irvine, the education campus. So next slide, please. So this new hospital that we're building, it's away from our main campus, which is really close to Disneyland. But as mentioned, it's right on the main campus of UC Irvine. So we're happy to be coming home to our academic campus in Irvine. So next slide. It's a beautiful new site. We have 2 of the 3 new buildings open, the Chow Family Comprehensive Cancer Center already up and running, as well as our Josie Wen Family Center for Advanced Care. The last building that is still under construction is the hospital with our emergency department, that one right in the back there. That hospital is targeting LEED Platinum. All of the buildings, though, are LEED Gold or LEED Platinum certified buildings. What's really special about this project is that it is an all-electric powered building structure. So the central utility plant that powers this site is an all-electric design with no carbon combustion. We're going to talk a little bit about that today, but the whole campus is designed with reduced lighting pollution, reduced water usage, and as we'll talk a little bit more about, heat recovery chiller powered and no carbon emissions of any kind. There is no carbon, no The central utility plant uses no natural gas to function. So this is a first in the nation of its type, and we're really excited to go live with this type of new facility for an academic teaching hospital. And this is just an overview. As you could see, this is a full-fledged teaching facility, 144-bed hospital with an emergency department, 8 operating rooms inside the hospital, with 18 minor procedure spaces in our Center for Advanced Care. In our ACC, our cancer center, there's 10 additional operating rooms for a total of 18 operating rooms. So this is a very intensive space, even though it is a smaller facility than our hospital in Orange. This is going to be a very intense, energy intensive building. So for all intensive purposes, this is going to be a high energy intensive building. So the fact that it is all electric it's groundbreaking, to say the least. Next slide, please. These are just some overviews of the structure, but if you go down Jamboree Road in Irvine, you can get a good look of how it looks in its final form now. And then just some key figures for the space, but again, these buildings are up and running and live now. And this is just a stack diagram. As you can see, it's a very, very robust structure. This building is again up and running. And then the last building here that you'll see, next slide, please. One more slide. The hospital will be up and running in about 6 months. One more slide. There we go. So this is the only building that's still under construction and will be finished sometime in July. And the activation for it is underway right now. So the 2 buildings, the Center for Advanced Care and the hospital, are connected with the ground floor that is our main operating center. That houses all of the operating rooms, our high intensity soil parts department, which is connected to our central utility plant via a tunnel, which houses all of the main piped medical gases and service utility lines. So very exciting structure. I'm really excited to be here and tell you this panel more about it. Again, did go over the timeline a little bit. 2 of the 3 buildings are already in full use, and then later this next year, actually late 2025, the hospital with the emergency department will be going live. That's the beam topping ceremony when we finish the structural steel of the main hospital. That was sometime late last year. These are some recent construction photos when they're putting the emergency department sign on the emergency department for the new hospital. And then here's some overviews of the, I believe, the chiller plants and the heating and domestic hot water systems, to give a little bit of an overview of it. Oh, and first, so the challenge, healthcare is one of the most energy intensive buildings in use. So as you can see, inpatient healthcare facilities are one of the most energy intense building types that we have. And then the type of energy used in those buildings, most of it is typically fossil fueled. So the electricity that is typically used inside of inpatient healthcare facilities, as most in America, would be natural gas. So going into this project, we wanted to see what different type of models we could utilize. Next slide. The central utility plant estimated demands and our goals for this project. We wanted to have for our outpatient facility, the EUI goal was just a little bit over 50 for again, the outpatient facility, and then for our inpatient facility, just a little bit over 100. As you can see, well below half of a typical inpatient and outpatient setting. So a traditional STEAM system for a hospital setting like this academic medical center, you would have a central utility plant that would be external with central steam boilers that are fired by natural gas with distributed steam lines serving steam processing, your kitchen and areas throughout the hospital. They're very inefficient with having to provide steam throughout the whole system. Again, powered by natural gas or electric, but it's found throughout most any hospital in America. Very typical and very tried and true. It's what we have here in Orange and probably what most hospitals in America of this magnitude are built with. So here in Irvine, what we're looking at it's a bunch of different types of technology. We have heat recovery chillers that are providing there we go. So the central utility plant model for this, we've have modular chiller or modular steam generators providing the steam for each component of the hospital, the kitchen, sterile processing, and the operating rooms all have their own humidifiers. So each little modular area provides their own zone humidification. This not only provides a more resilient system, but it's also much more efficient. We're extremely excited to test this new model, and we're already making plans to expand this model to our existing portfolio of buildings.
All wrapped up, Joe?
Yeah, unless there's any questions, sorry.
No, thank you so much for the overview. I think we will field the questions at the end after all the other panelists have spoken. Thank you so much. I'll introduce now Kenny Seaton. Kenny is the Director of Central Plant Operations and Strategic Energy Projects for the Cal State University Dominguez Hills campus. He's been there for since 2011. He manages the team responsible for heating, cooling, and maintenance of about 1.5 million square feet of building space on the campus. And I'm going to invite him to speak a little bit on activities to decarbonize the campus there. So, Kenny?
Also known as Kenergy. I just want to point that out, is it on the slide?
Thank you. First of all, how cool is it that we're building hospitals now that have no gas? Kudos for that. So our campus, roughly in the last 4 years since the CEOP program that Edison, that you can look up, we don't talk about it right now, but we've reduced our greenhouse gas by 50%. We've done that by electrification. We did get rid of some gas in the beginning, some direct gas-fired absorption chillers, but basically most of it was electrification, right? How do we run our buildings more efficient? And after we did that, 50%, then, what's next, right? So we're moving to the next step. And so recently in July, we just finished and started the commissioning of 21 30-ton heat pumps. The slide here shows how they're set up. There's 3 skids with 7 each. We connected them to the central plant heating loop. The idea is that if they can't produce enough heat, then we can always turn the boilers back on. But we haven't had to run the boilers since July. And so every day we're tweaking them and learning more and more. So I'm really excited to what does it look like next year? In the 5 months that we've got data for them, we have saved $10,000 in utility budget. So the difference between the gas and the electric, and about 250 metric tons of greenhouse gas in just that amount of time. We expect it's a 65% reduction in greenhouse gas from what we were running before. Next slide. When we design the system, first of all, it's not rocket science anymore, right? Heat pumps work, but you need to put some thought into how do you design them? Do your homework, that kind of stuff. Our system wasn't designed to say, hey, look, we're going to get rid of 100% of everything, because we just don't know, right? We would be overbuilding, or we would put ourselves in an uncomfortable position if it didn't perform, right? So we designed them to take care of 80% of our load. And we had an engineer that came out and looked at all the data. You got to have good data, right? So you know exactly what you're spending. What's your heating load? What's your cooling load? And we designed it around that. Now that that's being said and it's done, I truthfully hope that it's better than that, right? Because now we're seeing how we can run the buildings, and maybe we don't need 155-degree water to warm up a building space to 72. Maybe the 141, 140 that we're able to get out of these heat pumps is going to be enough. Next slide, please. There was a lot of lessons that we learned when we were doing this, right? I believe we're one of the largest heat pump projects on the West Coast for this style. And we were told all throughout the project, it's not too late to back off, right? We're not ready for heat pumps at that scale yet. But we did our homework before we did the project, right? We talked to people, we went around and we visited sites, we talked to manufacturers. Okay, why did they fail? And 90% of the time they failed because nobody took in consideration the delta P, the water that has to run through these, and the flow of water. They thought it was a plug and play unit. Heat pumps look like an air conditioner. They've got a pipe for the inlet and the outlet, and you hook it up to the system and it works. And it doesn't, right? Because there are some nuances that you have to understand. And so doing that homework was the crucial first step. We went and actually flew out to Sparta, Wisconsin. These heat pumps were multi-stack units, and we talked to the engineering team out there. We asked them, what do we need to do to design a correct system? Our design changed about 3 times while we had conversations back and forth with them. Okay, how are we going to do this? So you have to be flexible, right? You have to be able to shift and listen to what the experts are telling you so that you put the right system in. The DP was critical. What was the manufacturer preferences? What were their guidelines, right? We looked at all those things, and we designed a system around that. And it started up on day 1, and it worked, right? Like I said, our boilers have been shut off since July. And every day we're getting smarter and smarter on how we run those. Some of the things that we didn't expect was that my central plant chillers are also shut off now until almost noon every day for the last 2 weeks, because now that we've gotten colder in the daytime, heat pumps, they're not air source heat pump, they're air source or water source, right? And so we're running them to make hot water, which is that was the project. How do we stop burning gas for our hot water? So we put these systems in, we make hot water, that's why we're there. That means any byproduct of that, which is the chilled water, is free in my mind. And if we can produce enough chilled water, then that means the campus chillers, the 1,000-ton chillers that I use, don't have to run, right? So instead of running a 1,000-ton chiller at 150 tons or 50 tons, which isn't real efficient, right? When my chillers are running correctly, we're at 0.35 to 0.5 kW per ton. But when they're running at 35 tons, they're like 1.75 kW per ton. So now we're able to just shut them off, use them to circulate the water through the campus, take advantage of all the free tonnage that we're producing on the heat pumps. And so there's that huge byproduct there, benefit. Understand how the loop works. So if you're an engineer or something and you're designing one of these, you need to go out there and understand what their hydronic loop is doing, right? Do you put it in parallel? Do you put it in series? Those are questions that you need to know going into it so that you can have a successful project. But again, it's not rocket science. If we do that upfront stuff, these things work really good. Next slide, please. That's it. That's how simple it is. Thank you.
Excellent. And I think we're going to have a lot of opportunities, excellent information and many opportunities for follow-up questions after we hear from our next two speakers. I'll now turn it over to Dean Moreton. Dean oversees, he's the Chief Commercial Officer at Hydrogen Technologies. He oversees their commercial activities and expansion to capitalize on the ever-growing global demand for its breakthrough and zero emissions hydrogen boiler solution as a steam to hot water solution in commercial and industrial applications. Dean?
Thank you. Thank you, Mark. It's a pleasure to be here. I appreciate the opportunity to talk about how we've decided to use hydrogen, as Dr. Bauer talked about earlier, with the hydrogen network that's here in California, and use that to create steam or hot water. Now, what I've got here on this slide is just a quick show of how it's working, and then I'll go into where it's working. Basically, what we're doing here is we're taking hydrogen and oxygen, the two gases, keeping them separate, putting them into a burner chamber, igniting them into their exothermic reaction, which creates water. And that water is superheated steam. It's 5,000 degrees right at the tip of that red section. And what we do is we pass this steam through these pipes that's heating the water inside that boiler, and out comes hot water or hot steam into the reclamation piece. And then we can push that back to an electrolyzer or use it in a process somewhere else. And why can we do that? Because it's really pure water. We just created it. There's no iron, there's no minerals. It came from the two gases. We put it together. And that's basically what an electrolyzer does, the opposite. It breaks water into two. So what we're doing is we've got a lather, rinse, repeat process here where the electrolyzer takes electricity from the network. It breaks the water molecule into hydrogen and oxygen, stores it for us. We put it back together and hand it back to the electrolyzer. Next slide. So how does it compare to a natural gas? Well, on the one side, we got the natural gas boiler. And what you see here is it's got an air blower at the front of this thing. And we do this because we're trying to oxidize the methane gas that we're using for fuel. And to do that, we want the 20% of oxygen that's existing in this atmosphere we're breathing, and we force it into this boiler chamber, into the burner area. So 78% of that air we push in there is nitrogen, 20% is oxygen, and that's what we want. So we put 5 times the volume of air into this burner to get the oxidation, which creates the heat, which creates the steam. And on the backside of that, we got to blow that air somewhere. So what we do is we put it up an exhaust stack. And out that stack is coming that CO2, NOx, methane, benzene. That's the witch's brew of things that were created inside that thermal chamber of that boiler. And on our side, what we're doing is we're doing this oxyhydrogen boiler. We're using just hydrogen, just oxygen, no atmosphere. So the only two things that are oxidizing is the hydrogen and the oxygen, and it's creating just water. So that's where we're different in that we're not having to exhaust out all that extra air. We're not using the atmosphere. We don't have any any nitrogen. So we don't have any NOx output. So that's basically the difference between the two processes. You know, your fossil fuel is going to run that way, whether it's oil, natural gas, et cetera, versus our oxyhydrogen burner. Okay, so that's the technology. And where are we using it? So we've had the boiler up and running in California in Modesto for 7 years up to 2022. We've had the system being built in a commercial state by an industrial boiler manufacturer. It's called Superior. They've been doing that for 100 years. We've got the burner technology being done by another technology company, another 100-year-old company called Webster. And we're deploying this solution at the University of Colorado for their steam need to heat the campus. And why they chose this technology is because they've looked at other areas and basically decided that they want to have an opportunity to look at different areas of the hydrogen network, as well as how can they solve their decarbonization. Colorado has a NOx regulation that's very rigid. One of the things of Colorado is it's a vacation state. So when smog comes, the politicians don't like to have the mountains covered in smog, so they have a tight NOx regulation. University has to comply with this. And if they go above their NOx emissions, it's a financial penalty. So they are not excited about that. And our solution doesn't create any of the NOx, so they wanted to give it a try. So we're deploying it out there. They also said that the fact that we're using these 100-year-old companies with their existing support network made them comfortable, so that if something's wrong with the boiler, they have somebody nearby that can deploy and fix it, right? It's off-the-shelf components that have been out here forever, and it's well known within the supply chain of where to get it, how long does it take, and how's it put in. The other piece that they've been excited about was that they can take this hydrogen network, kind of similar to what California is doing. There's 7 of these things in the United States, these hydrogen hubs, and start to expand on how they can leverage the Swiss knife of energy, the hydrogen. They have the opportunity for the buses. They have the opportunity for fuel cell, where they can create electricity on the campus. They can use it for the hydrogen boiler. They can have an electrolyzer using their on-campus generation facilities. And Colorado has a $1 benefit to creating hydrogen from green electricity, which goes on top of the federal $3 credit for creating a kilogram of hydrogen. Illinois, Colorado are 2 of the states that have taken the carrot approach on top of the federal carrot approach, where they're incentivizing companies to try a technology that's different. And this benefit that the states and feds have put out there is similar to what we've had for wind, solar, batteries. The wind subsidy goes back 40 years, and we're still subsidizing wind turbines. That's why we can have solar, battery, and wind at such percentages across the US, because we've invested for decades in those technologies. Hydrogen's on the cusp of the same investment. The US is putting billions of dollars towards its investment. The EU, China, Australia, the Middle East are all investing heavily in the technology. And what they want is to drive down the cost of hydrogen, where we've got other solutions for decarbonizing environments. The thermal one's is a difficult one and tough to solve. And so hydrogen is one of those solutions. So basically, they wanted to take the path of cost reduction, looking at the trend out 10 years. Our Department of Energy says hydrogen will drop 80% in cost from today till 2030, 2032. And they want to take that as an opportunity to look at how can they decarbonize their buses, their thermal energy, their electricity generation, and how can they do that on campus. Further, they want to educate the students on this emerging technology. So they want to have the opportunity to bring in freshmen in the campus to understand how is hydrogen going to be used with their education system. So this gives them another venue to attract students and educate them on this decarbonization technology. Mark?
Thank you so much, Dean. I just would like to remind everybody in the room, if you want to submit a question, you could submit a blue comment card out in the hallway, and that will get us to us and anybody on the Zoom. We are also going to have questions. You can put those in the Zoom. We do have one last panelist that I would like to introduce. So it's my pleasure to introduce Lisa Hanneman. She's a senior account manager with Southern California Edison's Business Customer Division. She's led oversight and partnership with the State of California portfolio for SEE, which includes U.S. CSUs, California Community College, California Department of Corrections and Rehabilitation, and the State of California. During her time with SCE, she's been responsible for overseeing a portfolio of strategic and energy initiative customers spread throughout SCE's 50,000 square mile territory. She's the business customer lead for all business electrification initiatives and GHG-based pilot efforts. She had significant success in assisting customers with their goals in the area of energy efficiency, energy resiliency, and emission reductions. She's an active member of several key customer groups and committees in the state of California and has her Bachelor of Science degree from California Polytechnic University of Pomona. Lisa.
Thank you so much. We heard a lot from both Joe and Kenny kind of talking about the University of California and California State facilities and what they've been embarking on when it comes to decarbonization. Southern California Edison created the first in the nation GHG-based incentive program. And what that pilot effort did was it got us to a common metric. It took away what kilowatt hours are you saving, what gas therms are you saving, and it got it to what GHG are you able to reduce. And we did that at the master meter level. So we were able to take a look at what customers were doing at the meter and convert that to greenhouse gas emissions. And based upon that, we were able to incentivize customers for embarking on decarbonization. And when we heard a lot about what these facilities were able to do, you can see that technology is no longer on the bleeding edge. It's still on the cutting edge, but it's feasible. And whether you look at it from a new construction perspective or you look at it from a existing building perspective, customers are implementing and able to do so. There's two key things that go into that, right? How do we make them financially viable? And that's why this incentive pilot effort was really important. It not only helped them to change the mindset at their facilities and on campus, but it also gave them incentive funding to help accelerate the advancement of some of these technologies. And when you look at our University of California and California State University systems, along with a lot of other customers, but they truly are, kind of test beds and learning labs for these technologies, for these opportunities. And then in turn with that is it's allowing us as utilities, California Energy Commission, and other folks within the state of California to be able to bring incentive programs to the table that help to change the mindset and receive that commitment from the highest levels within these university and customer portfolios. And with that, I will turn it back over.
Thank you, Lisa, and thank you to everybody on the panel here for sharing experiences with decarbonization efforts. I just we're going to turn to some conversation and questions here. Just wanted to kind of try to synthesize where we are. Our first panel talked about some technology options for decarbonizing. Here we've got folks together who are kind of implementing projects at facilities and supporting those efforts to decarbonize. And so I think we want to hear from them a little more on what's behind that planning process, that decision-making process that allowed some of these projects to go forward. And what are the benefits they're seeing? And I'd like to hear some more about also what are the challenges that were faced and specifically how those were overcome. In my role at the California Air Resources Board, I focus mostly on reducing greenhouse gas emissions from heavy industry. When we're doing that, we're also always looking to support efforts that bring additional reductions in local air pollutants like NOx and particulate matters, and some of those were discussed here. And there's this trifecta of moving past combustion where we can reduce greenhouse gas emissions, we can reduce emissions of local air pollutants, and we can improve the air quality in the communities adjacent to these types of stationary sources. So I want to, turn the conversation over to some of the challenges and some of the benefits of implementing these projects and hear a little more about the decision-making process. So, aside from clean air, and I'm going to maybe direct this initially to Kenny and then hear from the rest of the panelists. In what ways do you see benefits from using zero-emission technologies in your projects? Beyond the clean air benefits, are there operational or other positives that you see?
Yeah, I mean, absolutely. And I kind of talked about that at the beginning, right? I'm not running a 1,000-ton chiller plant at 50 tons anymore. That's one of the benefits. It's cheaper, right? Once I was able to come up with the funding to do the project, I'm saving money. Another huge benefit is that I can't produce gas. There's no technology out there. I'm not going to drill an oil well and produce gas, but it is really easy to add 800 kW of solar onto my campus that will then offset the extra electricity that these heat pumps are using. And so now I end up one step closer to not just emissions net zero, but utility too, right? And so if I can produce that behind the meter, it also gives me other options, right? Well, let's say that, now we're producing too much electricity, right? Okay, well, right now it doesn't make any sense to run the heat pumps to make chilled water, but what if electricity gets super cheap because we're overproducing in the middle of the day? Maybe then it makes sense to fire up all the heat pumps in the summertime and not use the chiller plant that's efficient. It doesn't cost me any more, and in fact, it might cost me less. And so I think there's a lot of added things that, it's hard to really see all those right now, but they're showing up as we keep moving forward.
Mark, if I can also add, as a healthcare provider, the community externalities, almost outweigh the environmental. As a healthcare, I don't know how to articulate it well enough, but our whole intent is to provide health and well-being for our population. So the impact of not impacting our surrounding community by having less impact on them by our operations. I mean, we're very excited about that. The impact that our operations have on our surrounding community. We look at extreme heat events, especially where I am right now in Santa Ana, California. It's one of the most impactful events that our community sees. And a lot of that is just due to the impact on the grid. And we oftentimes have to run our emergency generators because of the lack of power available for the local community. The idea that our new campus is going to be lessening that impact on the local area and then lessening the impact on the local community is the whole reason why we are in business. So I think getting to the root of it, healthcare organizations have at the root of their business, we need to lessen the impact of our operations, and this is a great way to do so.
Thanks, Joe. So I'm hearing kind of good neighbor elements, alignment with broader goals, environmental goals, kind of ownership of the resources in terms of electricity, self-generation, and maybe loudest and most importantly, it's inexpensive. It can be cheaper. And I think that's a really important message that Kenny mentioned.
When it comes to the cost, are there incentives to transition to these zero emission technologies on the industrial side, or is it going to take environmental regulation to get there?
So there are incentives that are out there, and in fact, there are incentives available today. So when you look at our industrial customers and the opportunities to decarbonize their operations, their processes, we've got a program with the California Energy Commission called Indigo. That is available. It is focused on decarbonization and incentives specifically to industrial processes. And then we also have programs internally to Edison that are available to our industrial customers and the energy efficiency side as well.
And let me add to that, that the federal government has been implementing quite a few funds, grants, notes for decarbonization. California just won money for their hydrogen hub. They also won it for their import facilities. I see the additional benefits besides that grant money coming from the benefits of decarbonization, such that the board of directors or the regents can announce that their company is dropping in their GHG score. They can announce it in their annual reports, take a picture of it, talk to their customers, and say, we are achieving this decarbonization. If you're shipping into the EU, this becomes a requirement next year. If you're in the US, some of your customers of your products will be telling you, in such a case as one of our automotive companies, that they have to decarbonize, or the purchaser will find another company to make the product that they're currently buying. So the benefits are existential, as well as the good neighbor benefit. I'm seeing the clean air piece be beneficial even to the universities for attracting new students, because the new students coming in are asking, is my university clean? Is it decarbonizing? And it's a 17% of the freshmen waiting for what school they're going to attend based on how they're going to decarbonize. So I think Mother Nature's weather events have been echoing this decarbonization thing is really something we need to pay attention to. And not only the boards, but the regions are saying, we're making that happen and we're taking action.
Thank you. Appreciate that. And actually, while we have you on the hot spot, we do have some questions from our Zoom audience specifically about your technology. Our first question we have is electrolysis of water followed by hydrogen/oxygen combustion is an inefficient use of electricity. Why do this rather than use electricity directly?
So you've got a couple things going on there. You've got economics as well as efficiency. Having the ability to store and forward hydrogen is the first. The second is, where are we going with the cost of electricity over time, and where are we going to go with the cost of hydrogen? If I look back at my history book and say my wind turbines, my solar PVs, my batteries all had a trajectory of a learning curve of about 20 to 30% annualized. I think our hydrogen is going to go there as well. So the cost on the economic side is trajectorying down. How's it going to get there? No one in this room can say, right? Just like we couldn't tell you how did the solar panels get so cheap? How did the wind turbines get their prices where they are? And the batteries, we did it. It took a lot of investment, a lot of time, a lot of money, and that's where the economics have gone. So in terms of what's the cost to take that kilowatt of energy and make a BTU of heat from an electric boiler, that's a full tilt. Let's say you bought it wholesale and you paid $70 a megawatt hour for that unit of energy. If you happen to do it with green energy, the Fed would give you $70 back for that megawatt of use to create that steam. If you're in Colorado or Illinois, there's another $10 on top of that. So they're basically tilting the scale of economics towards what they want to incentivize. That's what I call the carrot. And on the other side is the stick. If you're in Washington or New York or EU, you get penalized for your emissions if you exceed your certain limit. So you have both efficiencies as well as economics. And at the end of the day, the people that are talking to us are saying, we're in business to make a product as cheap as possible, but we also have our board of directors or our regents telling us to decarbonize. So we have to balance these two things. And they're looking at the economics. Where is the cheapest way to decarbonize? And as everyone in this room knows, there's no one silver bullet. There's an application of many technologies to get to where you want to be at the end of the day.
Great, thank you. Really appreciate that. Talking about a lot of the economics and what makes sense. I have a different question. You know, we're talking end user perspective. Got a question from the room, just to talk about kind of these new systems and talk about maintenance changes and any challenges, the ability to train employees with the skills to operate this new equipment. Maybe we can start with Kenergy. Sorry, I like that nickname.
I like it too. Yeah, I guess every facility is going to be different, unfortunately. If you're a hands-on facility and you're able to do your own maintenance and you're there from the beginning, you know, you're part of the design, you're there while they're installing it, making sure that they do, you know, good piping practices and things like that. This equipment is going to come with warranties and technical support. You know, we have a laptop plugged into this that the company is looking at every day, and we call them up, hey, it's doing this, right? You know, we're not quite there yet. Or some of this is, you know, we're learning as we go, right? And so a lot of that is just education, right? We're doing things with the heat pumps that weren't designed for, right? People were like, oh, we're going to put this in for a building and it's going to produce cold water and hot water, and that's your set point and that's it. And we're like, no, I don't want to produce cold water. Like, what do you mean? You know, well, I want cold water when it's the correct time, right? So there's been a lot of software changes and stuff. But a heat pump is nothing but an air conditioning unit that runs backwards. If you've got smart technicians and refrigeration mechanics, there's only a few more components of that. Yes, when you get into the sophisticated software part of that, when we start talking about, oh, sometimes it's going to reject energy to the air and sometimes it's going to reject the energy to the water. And do I want it to focus on chill water or do I want it to focus on hot water? Those are things that, yes, you're going to have to work with the manufacturer to get built into the software. But at the end of the day, as far as, you know, my plant, all we're telling it is, hey, look, this is the set point and I want it to run. And all that other stuff does it by itself. And if there's a problem, I've got smart refrigeration mechanics that if they had to can do it, but right now it's too early. I'm still going to use the manufacturer's rep. I might buy the extended warranty for this thing to, you know, not have to worry for a few more years, but it's not cutting edge, right? I mean, some people would say it's cutting edge. I don't believe it is anymore, right? We've had heat pumps for years and years and years. I've got heat pumps in my tunnel that cool off the electrical room and make hot water for the building, right? How is that any different, right? So I don't believe the technology is magic or anything. It's kind of like solar, right? If you don't have solar, you think solar is this magic thing. And it's like, look, I'm sorry, it's a panel that goes on the roof that goes to a charge converter that charges the battery that runs your house. There's like 4 components. It's not magic, right? Everybody still thinks this technology is so out there and futuristic, and it's just not.
Great, thank you. Just didn't know if anybody else on the panel wanted to talk about training or challenges or hiring for this, using this new technology.
I like what Kenergy was saying. Same kind of dog, different fleas. You know, it's they're different plants for sure, but you're gonna have a lot of the same kind of problems. All I can say what we've seen is these are cleaner. They operate, you know, differently, but you're gonna have a lot of the same kind of problems. And when you're commissioning these spaces, if you're lucky enough to be building from a green site field, you know, we like we are doing now, we're there from the ground up. So we're recording a lot of the training activities from the manufacturers or the builders, so that our new employees are going to be able to you know, benefit from those training lessons and the installation videos from those installers, which is, you know, I think common with any project. So if you take those great practices that you would have with any new plant or any new construction project and apply those to these new types of facilities, you're going to be in good shape. But these are no different than any other complex building or utility plant. They're just different. And we've learned that. We just also have learned that it's a lot like an electric car. It burns a lot cleaner, and they're really a pleasure to work in.
And I will say just two quick things on the education side of things. So we're doing a lot of partnering now with California community colleges in developing certification programs that are specific to a lot of these new technologies. So now they're expanding, you know, their mechanical certifications, they're expanding their automotive certifications. You know, they're getting into these new spaces and developing certification programs that are available. And then, you know, we're also offering existing certification programs to existing facility managers, mechanical folks, electrical folks, et cetera. And I will say, you know, one of the unique things at Joe's facility there in Irvine is they actually kept around a lot of the folks that helped kind of implement the projects within the central utility plant, and their folks are learning side by side with them. And so, you know, there are certain things that are being done to get creative so everybody's ready and prepared as these new technologies are coming about.
Thank you all. And I'm going to turn to a question from within the room. Kevin from the Center for Strategic Policy asks a question to Dean. Can you please expand on your technology versus using turbines? My friends in the environmental justice world love the use of green hydrogen in fuel cells, but don't like using green hydrogen when hydrogen is burned, like in a turbine. Your technology heats the green hydrogen, but you say it does not emit NOx. Why is your technology different than turbines?
Okay, good question. So in a turbine, what we're doing is we're taking atmosphere and combining it with the hydrogen to create that flow of fuel to turn the turbine. So we're using green hydrogen inside atmosphere, adiabatic burning. And the temperature around there is about 3,700 degrees Fahrenheit. In our system, we're not using the atmosphere, so the nitrogen never is in the equation. We're using that 100% oxygen and 100% hydrogen that we just got from the water molecule that was split apart upstream, whether it was done in an electrolyzer or some other process. But basically, the temperature difference, as well as what is in the oxidation gases, that's creating the difference. So on the turbine side, if they were injecting just pure hydrogen and just pure oxygen, they wouldn't have a NOx emission. They'd have the same thing I do, just water. And there's no particulate matter or other pieces coming out from that system. But that's the difference.
So if I can just maybe state simply, you're burning the hydrogen in pure oxygen instead of air. Correct. And the nitrogen in the air is the source of the NOx.
Right.
Thank
Right.
you.
Great, thank you for that. I do have some more questions specifically for Lisa. Actually, one did involve students and training programs, and so you already answered that one for us. But we did have a question about the pilot program that focused on greenhouse gases instead of kilowatt savings. Can you expand upon that a little bit?
Sure. So our clean energy optimization pilot effort basically allowed customers the flexibility behind the meter. So they made the decisions on what should be implemented. It could be anything from energy efficiency to clean load growth to distributed energy resources, whether that was batteries, solar, et cetera. And as long as they showed the results at the meter, both looking at gas and electricity, and then we converted that to greenhouse gas emissions, they were then in turn incentivized. So we used the CleanNet short calculator That's what was utilized to actually get our hourly emissions. And then we bucketed them into TOU periods. So when you look at all of the hourly GHG emission factors, you know, that can be complicated. But when you ground it into how they see a time of use rate, so we bucketed it into TOU periods and then took the average greenhouse gas emission reduction emission factors for that. And that's basically how we looked at it and then incentivized them for whatever those reductions were. And so when you look at what was done at Joe's facilities, they were able to decarbonize. And then you look what was done at Kenny's facility, both in his central plant when he converted his gas absorption chilling to all electric. Those were all measures that were implemented that were provided incentives through the CEOP effort.
And I'll brag, we did $3.5 million in rebates through that program. So it was a great program.
And I can't let it be left unsaid that the source of the funding for these programs was the California Air Resources Board Cap and Trade program. There are auctions through that program that raise money for the state that gets distributed for various projects and programs, and this is one of many.
And those are two, very large facilities we're talking about. Are there resources for like smaller business, such as like a dry cleaner in California?
Yes, so we do have programs that are available. When you look at the clean energy optimization pilot, and what I will say is the reason we started with the University of California and California State University systems is not so much because they're large facilities, but because they have every type of facility you can imagine. So they've got everything from lab spaces to residential to commercial to education facilities. So you're able to take a very small building and basically implement the same thing, or you can take very large facilities, one master meter with 1 million square feet behind it. And as long as you use the same methodology, the methodology works and the incentives would be available. It doesn't matter at what scale.
Can I ask one more question, Michael? It's sort of a question for Joe that I had in listening to the development of the all-electric campus. And I was curious to hear about interactions in the development of that campus with the utilities, both electric utilities and natural gas utilities. And, just quickly, wondering if you could characterize or if there are any stories there.
There are many. Yeah, there's many. It was about a 6-year discussion, or it's been a 6-year conversation. The development on that site, it took a lot of time, and it was also unique to that site. You can't build this project everywhere. This is a unique project for many reasons, one of it being the location. The infrastructure in Newport Beach, California is highly developed. We're very fortunate to have SCE out there because it has a very robust infrastructure, but they still had to build up and develop for this plant. We're not able to develop any more for the next few years out there because we've maxed out our feeds for this site. But those were conversations we had during the development and through the programming of the project. We also are very fortunate to be co-located with our academic campus, and there's discussions about tapping into their loop on campus in the near future. I know the conversation right before ours was in the near future looking at their hydrogen prospects, and we're really excited about those ambitions and maybe one day tapping into that for our emergency power or things like that. Those conversations have already started because we have to plan for those things 10 years in advance. But the all-electric hospital conversation started, I believe, in 2018, 2019. And one of the first partners that we talked to was SCE, because we knew that this was going to be a major, they were going to be a major component and a major stakeholder in this endeavor. So if that answers your question, you know, they were along with us for the entire ride.
Yeah, thanks for those insights, Joe. And I think we are at 11:20, so we're going to look to wrap up this. I think, you know, we heard some thoughts on, again, technologies earlier, end users here. I'm always looking for the trifecta: reducing GHGs, reducing local air pollution, improving community health. That's what we're looking for here. We're looking to socialize that conversation. Electrification is a winning strategy for this, for meeting those goals. And I'm really thankful to hear about successful demonstrations of those. I think they're important for guidance. They're important for thinking towards future projects. So thank you to the panel for sharing thoughts. Looking forward, we got a panel coming up in 5 minutes, 4 minutes. Strong policies, clear policies are going to be needed to support these, and we're going to talk about some of those features. And I think some of the communication and partnerships across private, public entities are going to be important too, and that's part of what we're doing here. So thank you for your participation.
Great. Thank you, Mark. Thank you, Heather. Great job. Thank you to the panel. Let's get a round of applause. Appreciate you guys. Well, zero emission hospital, pretty impressive. And all of those heat pumps working out there on the college campus. So that's pretty cray, Kennergy, but great job and great work out there. Just so everybody else knows in context, because I know there's about over around 30 something people here in the room. So for those on the Zoom are like, that's it. But we had over 250 people currently on our Zoom, zooming in with us, so to speak, on this event. So close to 300 folks, just so you know, to give you some context. So thank you again. See you guys in a couple minutes. Now we're down to 3. So bio fast. Hey. All right, we're going to get started on the last panel here. I believe I already gave introductions to Sylvia, so I don't think we need to repeat that. So, and this is her panel, so take it away, Sylvia.
All right, thank you, Michael. So again, this is the regulatory and incentive overview panel. You've heard a lot today as we've talked earlier. And so the first panelist is Sridhar Siddharaman. So he is he received his undergraduate degree from the Royal Institute of Technology in Sweden, and his PhD from MIT. He spent most of his faculty career at Carnegie Mellon as the POSCO chair of steelmaking.
Your computer on Zoom?
No, mine's on.
Okay, is there still a problem? Okay.
Where's Heather?
It was Heather. So again, he started his faculty career at Carnegie Mellon at the POSCO chair of steelmaking with a joint appointment at the National Energy Technology Labs. Followed by a period in the UK as the TATA Royal Academy Chair of Low Carbon Technologies. Sridhar then served as the DOE as a Senior Technology Advisor at EERE. He's a member of the Secretary Granholm's Industry Technology Innovation Advisory Committee. Currently, Sridhar is with Arizona State University, holds a joint affiliate appointment at National Renewable Energy Laboratory, and is the CEO of EPIXC, Electrified Processes for Industrial Without Carbon, and DOE's 7th Clean Energy Manufacturer Innovation Institute. So please, thank you so much for joining us today, and we're excited to hear what you have to say.
Thanks so much, and thanks for giving me the opportunity to speak to you all. And just as a clarification, we don't do any regulatory work at all. We're a technology institute, so I guess maybe we would be in the incentives side, if anything. I guess we can go to the next slide, please. So what EPICS is, the acronym sounded really cool when we made it up, but it's difficult, it's a tongue twister to say it. It's really to look at industrial heating and for replacing all types of fossil-based heating with electric technologies. What we are is one of the USA manufacturing institutes, and we have some of them all across the country. Sesame in California, for example. So we are DOE's latest one, and I would say that we're probably the one that is focused on decarbonization as such. We are a public-private partnership, so we have around 150 industries, national labs, unions, and even some Native American tribes around the country as part of our consortium. Our federal budget is about $70 million over 5 years from DOE, and we're matched with state and industrial funds to at least have a minimum of 1-to-1 cost share with that. Next, please. So what we are targeting is the major greenhouse gas emitting industries. So industry is responsible for about 30% of carbon dioxide related emissions in the US. And half of that is just caused by 5 major industries. That's chemicals, petrochemicals, cement, food, iron and steel, and and paper and pulp as well. And those are the 5 industries that we are targeting. Next, please. And the kind of the levers that we are looking at affecting this is from DOE's industrial decarbonization roadmap that talks about the pathways for industry to reduce its emissions. And our focus here is process heating, and that too with direct electric based heating. So some of the work you heard about previously on heat pumps and boilers and things like that is very central to us. However, the premise of all of that is that you have green power available. So I would say that that is one of our goals as well, to be able to integrate accessible green electric power with industrial facilities. Next, please. So overall, our mission is that electric heating can be economical, and it supports manufacturing and decarbonization everywhere for everyone. And our mission, or what we work on, is developing at scale processes for electric heating for industry. Next, please. You can go to the next slide. Thanks. So the major challenge for us is the cost. It has to be done at a cost, and natural gas-based heating is it's been optimized over decades, and we have plentiful available of natural gas and its infrastructure around. So the kind of things that we are thinking about is how can we get the cost of electric heating to be competitive. There are variable costs associated with integration of renewables and risks associated with that. There's costs associated with capital retrofits or capital costs related to installation of electric technologies. Can we get those prices down? There are knowledge gaps associated with can you produce the same quality products, things like that. Now we have to bring all of that down. So those are kind of research trusts that we try and invest funds in. There are also added advantages that could bring your cost down. I mean, electric heating may allow you to heat where you want, however you want. So you might be able to make products that you couldn't do before. You might be able to flexibly switch from one product to the other that you couldn't do before. And you talked about air pollution. There might be, added advantages for communities in terms of healthcare costs, things like that, that you can factor into this as well. So essentially, our goal is ultimately to bring costs down to parity with natural gas, with CCUS. That's kind of our benchmark. Next, please. The economic models that our research would lead into, it's a complicated case because it's kind of a very dynamic situation, right? Everywhere in the country and around the world, the grid mixes is changing. So kind of the impact of electrification is changing dynamically as well. The costs associated with bringing that electricity into the factory, our grid system is changing as well. You have, distributed energy resources, different types of grids, all of that. Your economic models are also changing in terms of electricity trading and carbon markets. So all that has to be factored into our techno-economic analysis. Our biggest barrier might be the competition for that electric power that we face, and how much is industry actually going to get out of that from residential, transportation, and maybe our most recent threat is data centers. Data centers are growing by 12 to 13% per year in electric power consumption. And there's a lot less regulation in putting up a data center compared to a manufacturing plant. So is it causing a increased risk and move away for industry to adopt more electric power is something that we are concerned about. Next, please. So the trusts that EPICS works on, I would kind of split them into three broad categories. And I'm happy to kind of discuss more about this later on. But one of those is simply getting the power to the factory. What's the cost associated with that, depending where you are in the country, whether you're in the Pacific Northwest, which is very heavy in hydroelectric, versus a place like Arizona or California, where we might have a lot of solar, but that's intermittent. How do we integrate that with the actual manufacturing plant? The second thing is integration of that process heat with the process itself. Are you able to do it in a way that it costs least amount of risks for the plant? Can you use the same raw materials? Can you produce same or better quality products? Things like that. And finally, what do we need to do in terms of training the workforce? We have a lack potentially of high voltage electricians, or manufacturing expertise where you integrate electric heating as opposed to combustion-based heating. So how can we bridge that? Next, please. The sectors that I mentioned are, we target all the major sectors, and we are going beyond that as well. And this just shows the, cumulative effect we might be able to have operating at different temperature ranges and different heat duties. And the challenge is very different depending where you are. If you go to something like a large steel plant, you might be able to affect a point source carbon emission and electrification to a great extent. The technical challenges are extreme because you have to go to such high temperatures. On the other hand, you might be able to get more bang for your buck at the lower temperature range by simply, say, electrifying steam. It's such a cross-cutting problem that affects a number of industries, and you might be able to make a big shift or a big dent in your carbon emissions by kind of affecting that lower temperature regime. Next, please. So, essentially, I'll kind of stop there. That's just a briefing of EPICS, but ultimately we are part of DOE's Earthshot program in reducing 85% of industrial emissions by 2035. And our process is such that our members, our stakeholders decide on what we should be giving out our RFPs on. And, I invite you to join EPICS and be part of us. And we give out our funding opportunities every year, and we partner with states and industries and communities all around the country. I think that's all I had, and the next one just has my contact information. Thanks so much.
Thank you so much, Sridhar. That was very interesting. I want to remind everyone that if you're would like to ask a question or anything, to please go ahead. If you're online, go ahead and put your questions in the chat or fill out a blue card so that we can have some questions at the end. All right, so I'm going to go ahead and introduce the next speaker. So our next speaker is Kareem Hammond, and he's a policy advisor with the U.S. Climate Alliance, where he leads the Alliance industrial carbonization and short-lived climate pollution work and manages the Alliance policy database. Before joining the Alliance, Hammond completed a Master of Environmental Management at the Yale School of Environment, where he specialized in environmental policy analysis, clean energy systems, and industrial ecology. While at Yale, he worked on multiple projects and identified and quantified top decarbonization policies for implementation by U.S. sectors, including the 2019 America's Pledge Report. Hammond previously performed ESG research for San Francisco Mutual Fund and obtained a Bachelor's of Science in Environmental Science from UC Berkeley. Thank you very much, and we're looking forward to hearing your presentation.
Thank you for the intro. I'm going to actually share my screen since I have my slides. Let me know if that looks okay.
Yep.
Great. Well, thanks for having me. I wish I could be there in person in my home state, as you may have seen from my bio, and my hometown, actually from LA. But alas, I'm here in rainy DC, Washington, DC. So today I will be covering the state level perspective, looking across the country. To get there, I'll first give you a short overview of the U.S. Climate Alliance, if you're unfamiliar with who we are. Introduce just our emissions profile from the industrial sector and our work priorities over the past couple of years, a few key resources from the past 2 years we focused on, and then I'll close by offering some innovative state policies, in my view, that can carry this work forward. So the U.S. Climate Alliance is a bipartisan coalition of 24 governors that are securing America's net zero future by advancing state-led, high-impact climate action. We're geographically diverse, and we collectively represent 60% of the U.S. economy, 55% of the U.S. population. So with that majority in those two metrics, we have the power to transform markets. Launched in 2017 during the first Trump administration, the governors of Washington, New York, and California were our founding members. That's former Governor Jerry Brown, for anyone that's tracking. And we now include all of these states and territories you see on the map here. Membership in our coalition is not symbolic. States must commit to doing their part to keep temperature increases below the goals outlined in the Paris Agreement. And these are the 4 top line commitments that every governor makes by joining our coalition. And folks like me on what we call the Secretariat are here to support them. So as you can see, our work touches on most major policy areas you'd expect to see when you talk about the climate space on both the mitigation and adaptation side. And I specifically support our states on advancing work to reduce emissions from industrial sources. So that's inclusive of manufacturing carbon dioxide, all sources of methane, and the tricky super pollutant challenge of refrigerants. Okay, so how does industry show up at the Alliance? Well, if you saw the map, you probably noticed we don't include members of our coalition do not include Texas and Louisiana, where a large majority of certain sectors like chemicals and refineries are concentrated. So overall, the Alliance's industrial emissions are only accounting for about 1/3 of the country's total industrial sector emissions. Within our alliance, industry is about 11% of overall emissions, and our highest emitting sectors outside of oil and gas production are refining, chemicals, steel, cement, paper, food, and glass. So a lot of the same focus industries that EPICS is focused on, and that many other groups are focused on prioritizing to reduce emissions from. However, given the wide variety of industries that show up in the Alliance, our strategy has been to focus on cross-cutting solutions to advance high-impact decarbonization in the near term and into the future, rather than focusing on any one given industrial sector. We've also focused on both the demand and the supply side of the equation. So using the power of government procurement to create long-term demand signal for lower carbon construction materials through something known as buy clean policies. That's the market demand component. And then on the supply side, it's deploying state and federal resources for facility level decarbonization. So to that end, we've developed many resources and state level convenings on each of these priorities over the past several years, with a particular focus in the recent past on maximizing the billions in opportunities that came from the bipartisan infrastructure law and Inflation Reduction Act that went towards industrial decarbonization. Just to put a finer point on the federal side before moving on from it, I did want to reflect that this injection of cash into this space in the past couple of years has been momentous. It's really helped, or we've helped our members track and engage their stakeholders on applying for this money. But the reality is a lot of these programs have been tapped out and fully awarded. And a lot more investment is still needed to reduce emissions from industrial sources. So states can definitely play a key role in carrying this work forward, especially in areas that were arguably underinvested in these laws, such as industrial electrification. So to map out the policy options available to states in this complex space, we developed this policy guidebook a couple years ago, walking through a holistic universe of over 30 supply and demand side policies based on an extensive literature review and over 100 state level policy examples. We also identified specific pathways for those top 7 emitting sectors that you saw on a previous slide. To get a little more specific on policies, this is just an illustration of the menu of options and the number of examples we found at the state level. It is a bit out of date, I will say. This report was produced in the year 2022, and this space has moved rapidly. But this guidebook found that the single most common type of policy employed by states to date is financial incentives, which is unsurprising and it is good. But I'll note that most of these incentives only support efficiency measures and not necessarily other deep decarbonization solutions. And I don't have time to go through all of these in depth, so I'll just encourage you to check out the guidebook resources for a little more information. To help paint the picture of sort of what's next, I did want to spend my last couple of minutes highlighting a selection of different innovative policies in states in our coalition that get at both the demand and supply side of this challenge and both the regulatory side and the incentive side. So starting with incentives, this is the orange bubbles you see on the slide. California, of course, has several programs targeting industrial sector emissions and electrification, like Indigo and the Food Production Investment Program. I'm not going to spend a ton of time on those, given the esteemed panelist I'm sharing this with. But states like Washington, Colorado, and Pennsylvania have also developed grant programs and tax credits that are modeled after some of those major federal programs that we saw come out of the IRA. Colorado's industrial tax credit offering, for example, is essentially mirroring the industrial decarb project category of the 48C tax credit, while Pennsylvania's recently awarded $400 million RISE PA grant program is highly modeled after the $6 billion industrial demonstrations program. And then to close on the regulatory side, I did want to highlight a couple of interesting programs which are in those green bubbles. One is Oregon's recently finalized climate protection program, which sets enforceable emissions caps on fossil fuels used by stationary sources all throughout the state, including energy intensive industries. And another is Colorado's GEMM or GEM rules, which direct the state's manufacturing sector to reduce its emissions 20% by 2030. Technically, these types of industries are all covered by the emissions caps in California and Washington's cap and trade program and New York's under development one. Those are the blue bubbles. But there are definitely open questions about how to treat their compliance obligations in the near and long term. And that is a can of worms I will not be going into depth here. So just to conclude, the takeaway is that states around the US are deploying a mixture of what I call carrot and stick policies to incentivize emissions reductions from the sector. And there's definitely much to be learned, but also much to be built on. So with that, I'll say thank you and look forward to the Q&A.
Thank you very much, Kareem. We appreciate the conversation. I will go ahead and now introduce the next speaker. Next speaker is David Allgood with the California Air Resources Board. He works on the California Cap and Trade Program, focusing on industrial benchmarking and decarbonization of the manufacturing sector. I won't go into any more detail. We've already introduced him once, so.
Thank you, Sylvia. And also thank you, Kareem, for that. We work closely with Kareem and the U.S. Climate Alliance, and we use a lot of resources that they have made available. So I encourage you to look into those resources as well. I'll be talking about the California Cap and Trade Program through our Air Resources Board. Next slide. The California Air Resources Board is committed to reducing emissions and meeting our legislative and executive targets. We have already met and exceeded our AB 32 goal of 1990 emissions levels by 2020, and we are on path to meet our SB 32 goal of 40% below 1990 levels by 2030. We have detailed policies, regulations, and incentives in our 2022 scoping plan update, which details how we're going to meet our 2045 goal of carbon neutrality. This target was set by AB 1279 and requires an 85% reduction below 1990 levels of anthropogenic emissions, with the remaining emissions being counterbalanced by carbon sinks, including natural and working lands, and carbon capture, utilization, and sequestration. Next slide. As mentioned, CARB developed the 2022 scoping plan update that details a suite of policies required to meet these carbon neutrality targets. And key policies are described here in this slide, which includes the Cap and Trade Program. And I won't go into detail of all of these other programs, but I encourage you to review this slide further if you're interested in these complementary policies, especially just the scoping plan in general and just the overall statewide approach that we're taking to meeting these goals. Next slide. So on to the California Cap and Trade Program. This establishes a declining cap on statewide greenhouse gas emissions from major sources, and this covers approximately 80% of our total statewide emissions. We achieve this by directly covering electricity generators and imports and industrial facilities. We also indirectly cover transportation sector and residential and commercial sector by covering the upstream transportation fuels and natural gas suppliers. CARB issues allowances equaling to our declining caps that are set to meet our legislative targets, where one allowance equals 1 metric ton of carbon dioxide equivalent. Each entity covered by the program has a compliance obligation set by its greenhouse gas emissions, and entities are required to meet this obligation by acquiring and surrendering allowances and offsets. Because the cap declines, there are fewer allowances each year, and emissions therefore decline as well. This helps establish a steadily increasing price signal, which facilities addressing the lower cost carbon reductions first, and a long-term price signal to invest in cleaner technologies. Approximately half of the allowances issued are distributed directly to covered facilities for either ratepayer protection or leakage prevention, and the remaining half is auctioned quarterly. Next slide. And the revenue generated from the sale of allowances at auctions is then reinvested into our economy through the California Climate Investments, which provide a direct benefit to Californians. This program has received over $31 billion in auction proceeds to date. And as of November of 2023, these projects have an estimated emissions reduction of 100,000 tons of criteria air pollutants and over 100 million metric tons of greenhouse gas emission reductions. That includes nearly 600,000 individual projects implemented, and these projects include zero-emission vehicle rebates, expanded transit projects, affordable housing, and sustainable communities, with over 75% of the funding benefiting priority populations. Additionally, over $10 billion have been distributed to utility customers through on-bill credits. So some of you may see those credits that you get twice a year. That's part of the funding that's generated from our auctions, moves to the utilities, and then is passed down to ratepayers. Next slide. And lastly, we have a sister bill that came with AB 1279, which is AB 617, and that implements the Community Air Protection Program. And this program includes an incentive program as well as developing a publicly available technology clearinghouse. So if you go onto the website, you can see all of the technologies available to reduce emissions as well as meeting the rules and regulations. The clearinghouse provides transparent, accessible, accurate, and useful information to the public through a user-friendly system. This information provided includes requirements for new and modified systems, and CARB air district rules, and a list of readily available and emerging technologies that meet and exceed these rules, plus supporting documentation. So while the Cap and Trade program is a statewide greenhouse gas reduction program, these technologies being deployed are reducing criteria and air toxics throughout the state. And additionally, the funding that comes from these sale of allowances provide additional funding that focus in on these areas. So with that, thank you very much.
All right, thank you, David. It's always good to hear of how much money's been spent on incentives and reducing GHG and air pollutants. Our next speaker is Cody Taylor. Cody Taylor is the manager of the Industry and Carbon Management Branch in the Research and Development Division of the California Energy Commission. CEC funds research, development, and demonstration projects to meet the state's energy and climate goals. Prior to his work at the Energy Commission, Cody worked on energy policy at SoCal Edison and on technology development and policy at the U.S. Department of Energy. Thank you, Cody. Love to hear from you.
All right. Thank you, Sylvia. Thanks, everybody, for being here today. Glad to join you all. And I'm here to talk a little bit about some of our R&D and technology demonstration work at the Energy Commission. We are proud to fund a bunch of innovators in the state of California, putting putting technologies to use, advancing them, and helping us get closer to having the technology set that we need at the level of readiness we need to execute on our clean energy and climate goals. I'll say very briefly, the Energy Commission is, in general, the state's lead policy and planning organization when it comes to energy, and focuses on supporting all Californians and having a clean, reliable, affordable energy supply. I'll take the next slide, please. All right, unless the system is about to restart.
Four minutes, hurry up.
Yeah, we'll see if I can make it in under the wire. We can move on to the next one. I'll take the next. Thank you.
A hard copy of my slides.
Yeah, we'll see. So I am lucky to follow lots of folks who've already talked about technology today. So some of these types of projects have already been discussed. I know Rondo was speaking earlier. I'll just give a sampling of some of the projects we invest in our R&D and demonstration work that are germane to the industrial sector. So this is one example. Antora Energy is a company that is doing high temperature thermal energy storage, similar to what you heard about earlier from Rondo. And we see this as a good potential pathway to facilitating decarbonization and reducing criteria pollutants from combustion in a number of higher temperature industrial processes, as well as potentially providing support to the electric grid along the way. So we're happy to invest in demonstration projects like Antora's, where they're putting their technology into field sites and having it run in real settings that look like the industrial market out there. Next slide, please. This is another example. So Nalumbo this is a project that is in flight right now, as are basically all of those that I'll mention. Nalumbo makes an anti-ice coating. So this is focused on cold storage facilities, so large industrial cold storage facilities. Think about food chains and what we do to keep food cold at either refrigerated or frozen temperatures while it's on its way to the grocery store and to you. Those large refrigeration systems often have challenges with icing up of the coils in the refrigeration system. And so there are a few approaches to manage this icing. They tend to generally boil down to, no pun intended, heating up in order to melt the ice off. And Nalumbo has developed a new coating for those coils that can slow the rate at which ice forms on them and thus reduce the heating energy needed to de-ice the coils and the amount of heat that ends up in those cold storage rooms. So this is a technology that we are beginning a project now to demonstrate in a cold storage facility in California. I'll move on to the next, please. So Trevi Systems. Trevi is also heat focused, but at the other end. So this is a company that has developed plastic heat exchangers for use with low temperature heat in industrial settings. So heat exchange is used in all kinds of industrial and manufacturing settings in order to recover and reuse heat between different processes. The heat exchange that's used is generally made out of metal components, which are costly relative to other things. And so Trevi has focused on developing plastic heat exchangers that are thus significantly lower cost, because the extruded plastic can be made at relatively low cost and can stand up to use for over a significant amount of time, and because they're lower cost, they can be cost effectively installed to recover lower grade waste heat that might not be worth recovering if you were only using today's heat exchange technologies. So we're excited about this technology as something that potentially helps us see reuse of heat in more applications across the economy. I'll take the next slide, please, if it's still available. We heard about, excuse me, we heard about industrial heat
Like a
pumps
Bond film,
earlier. Yeah.
like a countdown to explosion or something.
That's right. We heard a little bit about industrial heat pumps earlier. Here's another example of that technology in action. So this is a project that we're also just starting up that is involving an industrial heat pump in a laundry facility. So industrial sized laundry facility, think the kinds of places that wash linens for big hotels or uniforms or things like that, do lots and lots of laundry. And this facility is installing a heat pump to, again, capture waste heat and reuse it. As you can imagine, there's a lot of heat that goes through the laundry process. And this is a real world application of these heat pumps. I'll take the next slide, please. So Hilmar, another project that we are just beginning. This is a dairy and cheese making company, and this too is a project involving a heat pump and a reverse osmosis system. They are going to be using these technologies together to reduce the energy required in their cheese making processes. There's a significant heat inputs to those processes, and they can address that in part by electrifying it via the heat pump, recovering some of the existing heat in the facility, and to some extent reducing the need for as much heat by using the reverse osmosis system to do some of the separation work that might otherwise be done by simply heating and boiling liquids in their facilities. So as well as electrifying heat processes in industrial settings, another strategy that we see as a viable path in some settings is eliminating the need for heat by replacing that with other approaches, other processes. I'll take the next. So Gallo Glass is another company that we're glad to be entering into an agreement with here. So this is a demonstration project that CEC and the Department of Energy are co-funding that will make about an 80% reduction in GHG emissions from a glass facility. So glass making is a very high temperature, heat intensive process, as you can imagine, to melt and form glass. And what Gallo is bringing is a process that can electrify most of the thermal energy requirement of that glass melting process. And so it's not completely eliminating the use of fossil gas in the facility, but it's eliminating a significant portion of it. And so we're glad to see demonstration of this technology that could make a big dent in, again, an energy intensive, GHG intensive process of glass making. Next one, please. So final project example here is another heat pump example. So again, we heard earlier from Atmos Zero, CEC's investing in this project to similarly demonstrate a steam generating heat pump in a California facility, a pulp and paper facility. Here too, we're interested in this technology because it can bring electrification via heat pump cost effectively to a higher temperature range than most previous heat pump applications that we've seen. So that allows electrification cost effectively of a greater chunk of the heat energy in industrial processes out there. So that's my last example. I'll just say about all of these, one of my esteemed co-panelists mentioned the Indigo program, the Food Production Investment Program, or FPIP program. These are just two examples of programs within our R&D division at CEC, where we are, as a whole, using the strategy of investing in promising technology pathways to advance the technology incrementally to be ready to be deployed in the real world. And one of the steps in that is coming to this demonstration stage, which are the examples I just shared earlier, where technologies are ready for prime time, ready to be built at full scale, operate in real plants, and show that they are a good investment for the folks who own those plants and that they succeed at what they're supposed to do of heating moving things, et cetera, while doing so in a way that is lower emissions and hopefully lower cost for their owners. So we're glad to be investing in that stage as well to help show that the technologies are ready and make it easier for future facilities to go and feel comfortable picking up those technologies, future financiers to feel comfortable making project loans to somebody who's going to do that kind of thing. And that's how we see these demonstration programs fitting into our overall technology strategy. So I'll stop there, turn it back over to Sylvia. Thanks for the time.
No, thank you, Cody. It was very interesting looking at just the range of the type of projects you talked about. So, I mean, that's very, very promising. So last but not least, we've got Michael Kraus. So he's the assistant, I don't think we've read his bio yet, so now you guys had to hear it. So Michael's the Assistant Deputy Executive Officer in Planning, Rules Development, and Implementation. In this role, he oversees stationary source rule development for toxics, criteria pollutant rules, CEQA, and AB 617 efforts. Michael started his career at the South Coast AQMD in 1991.
Hey, don't do the math.
As an assistant air quality engineer and permitting, working on a variety of air pollution sources. Then progressively, he got promoted to his current position. Over his 33 years, he oversees a number of rule projects, including regulation of refinery equipment, continuous equipment monitoring system, flares, fence line monitoring, combustion equipment, toxics, coatings, and adhesives, and upgrades to the flare event notification system. Michael's the lead for area source control measures for the 2022 AQMP and was instrumental in the development of the 2012 and 2016 AQMP. Earlier in Michael's career, he wrote dozens of CEQA documents, as well as leading the effort to create the California Emission Estimator model used statewide. There you go.
Thank you, Sylvia. I love it. Earlier it was beer and now it's cheese. I mean, it's lunch. Okay. My presentation won't be that riveting, but it is very important to us here locally here in Southern California. So we just want to touch on the efforts we're taking here locally at the South Coast AQMD when it comes to zero emission standards, incentives, et cetera. So let's jump right in. Okay. So I don't really think we need to kind of touch on this slide for those folks that weren't familiar with us. We thought we'd just sort of do that intro, but I think at this point you're familiar with my intro I gave a little earlier about who we are at South Coast AQMD. Next slide, please. Okay, so as I mentioned earlier, in order to reach these goals, we set forth a plan, what we call Air Quality Management Plan, to sort of take a look at these standards that are set by the federal government and whether we're meeting them or not. So far, there are 4 ozone standards, and sad to say, we're not meeting any of those. And we're not meeting a PM standard either, but let's move on. Okay, so in order to try to make those reductions, as we talked about earlier, we look at all those possibilities that are out there, and zero emission has a great wealth of opportunities out there, and in particular, a number of sectors that we've set forth in control measures within the plan. So I'm going to talk about those a little further. Next slide, please. So with regards to some of our rulemaking, so one of the first rules that we took a look at was commercial bakeries out there. So these are like just large sort of industrial type settings of large bakeries. Yes, Thomas's English Muffins right here in Placentia, a few miles away from this office actually, and various other groups. And it was a real learning curve for us, a real learning experience about the different types of opportunities out there that these folks can migrate their baking and cooking ovens into more zero emission technologies. We also learned there's various different types of ovens and things, from smokehouses and coffee roasters to tortilla ovens as well. So, and as we craft rules, it can be a very interesting journey, and looking to see how those different types of applications can be utilized and where the challenges are at, and we can work within our rule development to kind of carve out those sort of niches. Okay, next slide, please. But ultimately, we were looking at zero emissions and where we can find those opportunities possible. In other areas, such as our commercial water heating rule, 1146.2. Yes, there are other 1146 rules, in case you're questioning what the point 2 is. We have 1146, 1146.1. Basically, the idea is that we concentrate our rules on the very sizes of these types of equipment, and then we can kind of narrowly focus in on those uniquenesses of those types of, in this case, BTU rating of those. So So these would be considered more on the smaller scale, so to speak, of those types of water heaters, but still considered commercial, but actually all winding down even to some residentials because you need a lot of BTU to heat up your pool. So there's a lot of different types of equipment that we looked at with this rule, and we set forth zero emission goals with these rules. And again, we had the opportunity to understand a little bit of, again, where those are more easier opportunities we believe that are there, and one of the more challenging opportunities are there. And we utilize things like implementation dates or alternative pathway options for folks to take if they run into these hiccups or these challenges and try to meet those standards and meet those targets we have set forth in the rule. Next slide, please. So currently we're working on, you might be familiar with some of this, so we're getting some media coverage on this when it comes to our residential space and water heating rules. So two separate rules there, but we're working on both those together and hopefully bringing those forth to our board. Popped on a couple little pieces of information here. Some of our preliminary draft rule language and our staff report is available online. We've been, as we always do with our rules, we work with our stakeholders and we go through an iterative process and hearing back from them, reacting to that, responding back to those things. So along with that, we'll have revised versions of the rules and update our staff reports along the way. Again, it's a public process. We've been doing this over a year now, but we've been talking about this for many years. So, as Sylvia noted, there's other previous air quality management plans that we've actually introduced some of these concepts there, may not have fully implemented them. So as we kind of go along, we continue to learn more, reintroduce them as newer plans. And so again, this isn't really like a new subject per se, but we're now getting down to the wire and actually looking to get to those actual details, and we'll see what happens. We have held a number of working group meetings as well. If anyone's interested, we do have all this information is all available online. All the rules that we work on actually are under our proposed rules page. There's a table there that lists out all the rules we're working on to amend or seeking to adopt. They're done in numerical order along with the title of the rules. Just click on those, takes you to another page, and all this great information is there. Next slide, please. Some of the upcoming rules, as I mentioned, is 1146, 1146.1. Again, where these do tier off of control measures. That's the term we use when we set forth strategies in our air quality management plans. And as you can see, they're different sizes, and we'll be looking at, we've already actually started the rule development here for both of these rules. And again, evaluating all the feasible options that we have when it comes to zero emission technologies. Next slide, please. So the other thing I want to touch on is our incentive programs. And we had an incentive program before. Going back a little history here. We had a furnace incentive program. We set forth $3 million to try to incentivize people for lower NOx emitting equipment. So at that time, to give you boring details, 40 nanograms per joule. We're ratcheting this technology down to 14. So we see a lot of emission reductions, a lot of great opportunity. And so we sent a lot of money out there to try to incentivize people to do early deployment of that. As we were doing that, we recognized that people were really interested in heat pumps and installing those. So we started to switch gears and we started sponsoring more money, $3.5 million, into folks switching out and going into heat pump technology. Within 1 year, we had 2,500 homes in Southern California switched over to heat pump technology, and the consumers were pretty pleased with that technology. So it really kind of gave us an insight as we worked into the plan that not only are we getting consumer acceptance of this, actually the manufacturers were encouraging us. They were out there saying like, hey, don't come out with a plan to ratchet it down even further from 14 down to 7, because that means we got to go back into the lab. We need to do research and development. We're going to have to spend millions of dollars. We're going to need consumer acceptance of these types of things. We already create and manufacture successfully heat pumps, which give you zero emissions. So it just makes logical sense for us to make that a goal and a target, which is, of course, what we're doing right now. Again, as we learned from our furnace rebate program, getting people into heat pumps, we decided to create a new program called Go Zero. And we, again, starting from the beginning here, we started looking at where are the opportunities and where's the need, right? So of course you have single family homes, but these rules will also impact things like multifamily homes, apartment buildings, like commercial buildings, small businesses. And so all of these areas we decided to support and are generating this fund program program for all of those areas. Some folks have also recognized that, like, hey, I've been an installer of natural gas furnaces. This has been my bread and butter. This whole idea of installing heat pumps, getting involved in the electric world is something different. So then we recognize the fact that folks out there need some training. And so we wanted to fund those types of program as well. And then finally, outreach. None of all of this is moot if people don't know about it, right? And so while we try to do our best out there to, provide pamphlets, to keep talking about these in public forums, have website information, et cetera, sometimes it just takes someone out there in the front line. So there was a suggestion from one of our board members to actually incorporate as part of the program an outreach and even an application assistance, having people sit down with them to work out applications and look for other funding out there. There's a whole mess of other funding out there that you can stack with our program as well. And again, some people just don't know about these things. We try to do our best to create these clearinghouse information, but sometimes it's much more effective if you have somebody who's actually out there. And for Southern California, frankly, to speak the language. So to speak in other languages besides English in order to get the message out there. The fund is looking at a total of $21 million right now. We do consider this quote unquote a pilot program. Our executive officer has talked about seeing how the program works and seeing what kind of next steps and decisions he wants to make to continue to expand that program. We're really looking forward to making that happen. Right now, we actually just finished doing a contract bids, and we're about to announce some of what we hope are going to be our proposed awards to those companies that are going to assist us in rolling out and implementing all these elements of the program. In addition, our board is very interested in ensuring that the disadvantaged communities get sort of front row priorities on these. So right now we're trying to target a goal of 75% of this funding to go toward those disadvantaged or we considered overburdened communities. And for the sake of timing, we're trying to get this to our board right now. We're going to be presenting actually next Friday to our board on the staff proposal and recommendations and hoping to launch this program early next year. Next slide, please. And that was it. Okay. Back to you, Sylvia.
All right. There was a lot of information there. So actually, I have a quick question for Cody. When you were giving your examples in your presentation, there was a lot of unique types of industries that were involved, and I just wanted to know how do you recruit these companies to come and take advantage of the incentives?
Sure. So our process for those programs that are talking about the R&D and demonstration programs, because we don't have sort of larger ongoing incentive programs in the industrial space. We are generally focused on the technology providers, so the companies developing the technologies, and we're putting money on the table in a public solicitation and asking them to come in and bring a customer, essentially. So they're coming to the table with customers who they think they can make a sale to or have made a sale to, assuming that they can pull in a CEC funding to match it.
Okay. I think that's, it's very helpful. I mean, it's great that like I said, that there was a lot of variety in the examples that you gave. So we did get a question. And so incentives are a very, very big part of the climate tech adoption. But for industrial sectors, operating costs are much more important than capital costs. Are there any operating cost incentives? Does anyone?
Well, I'm gonna one thing I try here. So actually, for locally industrial sources are required, or actually any really emitting source that's considered a stationary source is required to come in for us for a permit, and those permits can be pricey. And they pay annual operating fees, et cetera. However, if you're a zero emitting piece of technology, you're not creating any air emissions, you do not need a permit, and then you do not actually pay then for the renewal of that permit, and you're not paying emission fees. So we actually have a process by which one pays for how much they're emitting. It's an incentive to reduce those emissions. So basically, for the local agencies, I think a company should know that that's an incentive for them to drive towards zero emission.
Does anyone else want to add to that? All right, it was a tough question. All right, so I actually have another question here. So I think we've heard from all the panelists that costs are definitely a barrier. So what zero emission incentives are out that are out there are really working, or what types of incentives would be helpful to get this technology out there more?
Zero emission comes at a cost. No, so, one of the things that we've been finding is that, there are challenges to do what we consider fuel switching. So going from your fossil fuel that everyone's used to something like a zero emission, whether that zero emission is due to like a hydrogen fuel cell or solar or electric heat pumps, et cetera. And so a lot of times people talk about just the importance that there's the necessary supply out there when the demand needs to be met. So definitely incentivizing those groups that have more control over these things, like an energy supply route, because I know we get challenged as an air agency. We're not a utility. We don't generate the electricity, but we're relying on that in order to have a successful program in order to meet those zero emission goals. And so, incentivizing things, that help basically infrastructure and upgrades. And I know we worked 1146.2. A lot of the companies that we met were like, we'd love to do this, but like, we need to make sure our panel, which is being, driven by our electric, utility, is there and getting us what we need, and doing those updates and on time kind of thing, because things get really, behind. So, we find that.
And I would just highlight that please talk to your legislature, because the over $31 billion in proceeds from our auction that goes to the Greenhouse Gas Reduction Fund, and that needs to be appropriated by our legislature through a budget process. And then that goes into these other programs. But so it's really important that getting involved in this to try to set these programs up would be very beneficial.
I'd suggest the needs vary a little bit by industry also. So in some, the access to power, if you're electrifying systems, is going to be a significant barrier just because of the scale of individual facilities, that you're replacing so much heat with electricity or electric-driven process that the wait for an interconnection upgrade with the utility may be a significant time delay in your project, which is significant costs in the way that time is money in project development. For some industries that are made up mostly of smaller entities, think of the food processing, smaller end of that market, or the laundry facility example. The barriers there may be more around knowledge of the technology options that are available. And so programs that are focused on helping through an assessment process that can help a facility understand what their options are. If they want to make technology upgrades, that may be the sort of key to unlocking progress in some parts of the industry. And others, the simple scale of the capital investment needed, think about cement and decarbonizing and reducing air emissions from cement plants. They're gigantic. There are a very small number of them. Capital investment there to entirely switch process can be extremely expensive, hundreds of millions of dollars. And there's not been a sort of history of project finance as a mechanism there. So if someone's bringing a new technology to market in that industry, they may need some other financial mechanisms that are not typical in that industry in order to execute on scaling up delivery of that technology.
I think we definitely need some more dollars for sure. Go ahead.
Oh, yes. Sorry. I was just going to add that agree with what all the speakers said about cost, but I did want to just point out that not every intervention in these sectors is cost negative at this point. The DOE, in their Pathways to Commercial Liftoff report, identified plenty of like cost positive interventions that can be taken, especially on the efficiency side of the decarbonization pathways for their 8 subsectors of focus. That cumulatively added up to about what is it, 80 to 150 million metric tons of abatable emissions nationally from 8 major manufacturing sectors could be done at essentially zero cost interventions, because the interventions would save operators money.
The only thing I
Thank
would add perhaps is
Go ahead.
the integration across the supply chain. So if you look in Europe, where some of these things have worked out, say north of Sweden, it's because there's a certain degree of integration, and customers are willing to pay for green products such as green steel. Automotive manufacturers and even utilities are able to share that cost. So that kind of symbiosis might be a way to also de-risk the costs. Or if you look at, say, Denmark, heat pumps and boilers, to some extent, it's been integrated with things like district heating, so that you have symbiosis with other sectors that might de-risk your investment, which I don't think we do enough in the US of.
Good point. All right. First of all, I want to thank all of my panelists here for a very interesting conversation today. And I'm hoping that we can move the ball forward of getting more incentive money and thinking about other types of incentives to get these projects on the ground. So I'm going to go ahead and pass it now to Michael and Mark for some closing statements.
Sure. Thanks, Sylvia. And thanks everybody for coming here to the South Coast AQMD. And we're really happy to have hosted this conference and to have the opportunity to present it to you today. We hope folks have learned a lot. Again, we've got about 300 participants in the workshop. So we're really excited about that attendance. And again, thanks everybody for attending and participating and giving us great questions. But you're not done yet. We're going to have some closing remarks from Mark.
From the CARB perspective, also just want to say thank you to all of the panelists who participated and to the team that pulled the event together. Very helpful. And just want to, highlight maybe some of the lessons that I heard today. Again, there are really good options out there. They're not out in the future. They're available now. We heard some really good success stories, and there are challenges associated with them, but we know that those challenges can be overcome through kind of clear policies, through our working together as public agencies across with private entities to coordinate and make sure that there's a runway for these projects to be able to take off. So I'm just hoping that we're leaving this with a sense of optimism towards we've got these technologies. We've seen projects going forward. We're socializing them and communicating and collaborating together, and we'll hopefully through that be able to see more. And I think this is part of that. And I think we want to keep that conversation going. So I know that I'll be available to people who are interested. There are lots of resources online. From some of the panelists who have spoke today have done a great job of pulling together funding sources, incentives, and other options that are available to support projects like this. So hopefully we're building momentum to implement more projects that can reduce greenhouse gas emissions, reduce health-related pollutants, and continue to improve the air quality in our neighborhoods. So again, thank you. And I think I maybe have the last word.
Awesome. Thank you so much, Mark. Appreciate it, and appreciates everyone attending. All right. Take care.